It says it's streaming on YouTube.
Yeah, it's streaming on YouTube. So
okay, so once again, I'll just say we're delighted to have Stefano to talk to us today about ADS3 holography and what it can tell us about black hole microstates.
Okay, thanks a lot. Okay, thank you very much for this opportunity and of course for organizing this event. Okay, I hope you can see the screen. Okay.
Very well. We can see the whole screen. We can actually put it into display mode. Maybe it's better.
Display mode is like this. Okay.
Control L, I think. If it's a PDF.
Yeah, that's what it was before. That was full screen mode, which was.
We don't see that. It seems like you're maybe showing just the window rather than the full screen.
Yeah,
but
but
it didn't change when you went into reading mode.
Yeah.
Okay, sorry. Maybe should I stop share and share again?
Yes, but choose the thing that you share to be your desktop or something, and then.
My desktop. You want my desktop? Okay.
Well, yeah, so long as there's nothing bad on it. Now put it into full screen mode, and it should work.
Okay. Now I put it into full screen mode. Okay, is it better now?
Much better.
Perfect.
Okay, good. Then, okay, finally, sorry for this little delay. And okay, I think I can now start. So today I'm trying to talk about this, some not so recent work on heavy light for point correlators. So it's work that has appeared essentially in late 2017, but I'll also try to sketch some work in progress on the Regge limit of these correlators, which is, as I said, still work in progress. I will probably also have to touch upon some related material, okay, which is contained in this series of papers. And here's a list of the people that in various configurations have contributed to these developments, okay? So I'll give you some motivation first. So we all know that in some situations, a black hole is dual to an ensemble in a two-dimensional conformal field theory. Okay, so the typical paradigmatic example is the by now very familiar in this conference D1 D5P system, okay? So which is nothing but the original Strominger and Vafa black hole. So that black hole admits a decoupling limit that contains an ADS3 factor, and so it is supposed to be dual to some two-dimensional, holographically dual to some two-dimensional CFT. Now, in this perspective, black hole microstates are described by heavy operators, and when I'm talking about heavy operators, I will always mean operators whose conformal dimensions is of order of the central charge, okay, which I'm of course taking to be very large. Okay, so this condition is equivalent to requiring that the mass of the corresponding black hole is of order of the inverse of the radius of ADS. Okay. So we know that at least some of these heavy states, okay, which for the moment are states that do not capture the whole entropy of the D1 D5P black hole, but at least a family of these heavy states is described by a 10-dimensional classical geometry, okay, according to this paradigm, which was first suggested by Matur, which of course is the usual fuzzball paradigm. So these 10-dimensional classical geometries have, okay, here I'm just showing the three-dimensional part of these 10-dimensional geometries. They have a boundary which is ADS3, and then at least if you choose some particular, let's say, hierarchy between the scales, in particular, if you choose the momentum charge QP to be much smaller than the D1 and D5 charges Q1 and Q5, then in this regime, you can distinguish a very near horizon region in which the ADS3 becomes a long ADS2 throat. And at the end of this ADS2 froth, which, as we will see in the solutions that we now know, can be made arbitrarily long. Okay. At the end of this froth, there is the geometry ends in a smooth, what we call a smooth cap. Okay. So this situation is, of course, very different from the usual extremal BTZ black hole, where the froth instead goes on forever, okay, and ends in the horizon. Okay. So, given this semi-classical description of the microstates, what I want to do today is try to probe these microstates using light operators as probes. Okay? When I'm talking about light operators, I mean operators whose conformal dimension is of order 1 rather than scaling with C. Okay? So think about any single particle, for example, chiral primary operator, okay, which I will denote as O light. So in particular, one can compute 3-point correlators made by 2 heavy operators and 1 light operator. And these 3-point functions have a holographic interpretation as a 1-point function computed in the geometry. Okay. As we will see, to extract these 1-point functions, it is just enough to expand the geometry around the ADS boundary. Okay. One can also consider another class of observables, probably more interesting, which is represented by 4-point correlators. So correlators where you have 2 heavy and 2 light operators. These holographically, these 4-point correlators correspond to 2-point functions of the light operators computed in the microstate geometry. Okay. So to extract from the geometry this 4-point function, you have to do something a little bit more difficult than before. You have to compute, you have to solve a wave equation in the geometry. And as I said before, I will also try to show that in some limit, okay, which is what is called the Regge limit, okay, this problem actually simplifies. So it reduces to a simpler classical problem, which is represented by a geodesic in the geometry. So more precisely, you just have to consider a null geodesic in the geometry. And as I will describe later, this let's say, geometric, this bulk picture precisely corresponds to some, on the CFT side, to some kinematical configuration, which is described by this, by taking this analytic continuation. Okay, so this is something that I will again describe better later. But essentially, in this, so in this page, I will show you all the things that all the topics that I would like to discuss in this talk.
Stefano, to go from the correlator to the geodesic, the Regge limit involves taking just very high angular momentum on the sphere, or do you have to take some high energy or high momentum in the ADS?
So from the bulk point of view, it corresponds to take high energy at fixed angular momentum, if you want, at fixed impact parameter. Okay. So that's the bulk interpretation of this Regge limit. On the CFT, it just corresponds to take this configuration of the points where you insert the operators on the CFT side. Okay? So, but as I said, I will come back to this, okay, and I will discuss this hopefully in a little bit more detail in the later slides. Okay, so before I go into the details, I actually like to highlight what we hope to learn. Okay, what we have already learned and what we hope to learn from this approach. Okay. So for the moment, we have mostly concentrated on cases where we already know the classical geometry. Okay. So this is, of course, the easiest thing to do. Okay, consider the cases where you can construct a geometry dual to this heavy state. Okay. And in these cases, these let's say, holographic perspective has helped us to construct a precise map between states and geometries. So now we know very precisely how to associate a state to each one of these geometries that we have constructed. And this holographic map is also, I think, could also be used to argue that the geometries that we know are really dual without any reasonable doubt, I would say, to some particular states of the D1, D5 CFT. We can also check using these computations the consistency of the gravitational description of the microstates with unitarity. For example, one can check that the 4-point correlators that are extracted from the geometries do not decay when the Lorentzian time becomes large, okay? Which is something which is required by unitarity, and it's something that instead wouldn't be true if we use the naive black hole solution. And then, as a byproduct, these methods also give us a new way to compute holographic correlators. Okay, correlators that involve both multi-particle operators, like the heavy operators that I discussed, but also, in some limit, the usual single particle operators. Okay, so for example, if you want to compute the usual 4-point function with 4 single particle chiral primaries, which are the typical 4-point functions that people have computed since the early days of the ADS-CFT correspondence, people have used typically Witten diagrams to compute these 4-point functions. Okay. We will show that instead, knowing these dual, let's say, microstate geometries, we can perform these computations without bypassing Witten diagrams techniques. So it's a really new technique if you want to extract these correlators. Now, probably more interesting is the case where we still don't know the geometry. So this is, of course, what we would like to understand is how to complete this program and understand how we can provide a gravitational description for the states that we still don't know how to describe gravitationally. Okay. So you could ask if this point of view could be useful also for this. Okay. Now, I think it would be useful. And for example, this CFT intuition has been a guide, even until now, okay, has been a guide in constructing the dual geometry. For example, in the construction of this superstrata that has already been described before by many speakers, but that I will also briefly review later. Has been, so the construction of this superstrata has been very much inspired by this CFT perspective, okay? So I think that this point of view will also be a useful guide for constructing hopefully new geometries, okay? But probably the more important and main open question, to which I still don't know the answer, so I still don't know if the answer will be positive or negative, but let's say the real hope is that using general consistency requirements of the CFT, okay, consistency requirements like unitarity or consistency of the bootstrap or something of that sort, could give us a hint for understanding if and how the structure of the classical horizon is has to be modified for typical states. Okay? So this is the real motivation that drives this program. Okay? As I said at the moment, this is still something that we cannot really make completely concrete. Okay, but we will try to let's say build tools towards this goal. Okay, so I think I've ended this first introductory part, and now let me start to discuss really give you some details on the computations. Okay, so the D1, D5P system should be already familiar to everyone, so I can just briefly introduce it. Again, it's so we consider T2B string theory compactified on S1 times T4, and we take some D1 and D5 branes and we wrap them on the S1 and the T4, and we also add some momentum along the common directions of the D1 and the D5. The naive black hole that you obtain, as I said before, as a near horizon limit, which is ADS3 times S3 times T4. Okay. For all the purposes, for what I'm going to say today, the fact that you could safely replace T4 with K3 and essentially nothing will change. Okay? So I'm just describing T4 for concreteness, but the story for K3 is exactly the same for the purposes of what I'm going to say today. Now we will take the volume of the T4 to be string size, but we will take instead the radius of this extra S1 to be much larger than the string size, in such a way that the proper description of this system is in terms of a two-dimensional CFT living on this S1. And this CFT is the well-known D1D5 CFT, which has 4,4 supersymmetries and has a central charge C given by 6 times the number of D1 branes and D5 branes, so 6 times capital N. So it could be important for us to keep in mind that the CFT has a modular space of marginal deformations. And in this modular space, there is a point, which is the so-called orbifold point, where the CFT description becomes easy, okay, where it's easy to have to form an intuition based on the CFT. This point corresponds on the gravity side, however, to ADS spaces that are very much curved. So ADS spaces whose radius is smaller than the string length, while, of course, to understand issues regarding black holes, we are actually interested in a very far away point in the modular space, which is some sort of strong coupling point where actually the radius of the ADS becomes much larger than the string size. So I will try to use as little as possible of CFT, of these orbifold CFT technologies. Essentially, I will only need to use the symmetries of the CFT. And this CFT has the usual Virasoro symmetry, which is generated by the Virasoro operators L. It also has an SU2 times SU2 symmetry that corresponds to, on the bulk, to rotation of the S3 sphere, which is generated by the currents J and J theta. And then, of course, it has the supercharges. So 4 left moving and 4 right moving supercharges. As I said, at the orbifold point, the description simplifies. The theory becomes a sigma model on this orbifold space, T4 to the n mod Sn. And at this point, you have a bunch of free fields, which are 4 bosons and 4 fermions. And since it's an orbifold CFT, you also have, importantly, these twist fields, okay, that are an important ingredient in constructing the states. So the most important states for us will be these chiral primary operators that are operators whose conformal dimension is equal to the R symmetry charge, okay, H equals to J, okay, and H bar equals to J bar. And the important properties of these chiral primary operators is that their conformal dimensions and their 3-point functions are protected in the sense that they don't depend on this moduli of the CFT. Okay? This is true for the chiral primary operators, but also, of course, for all the operators obtained by acting with the symmetries of the CFT on this chiral primary operator, so on these descendants. So given these, let's say, ingredients, now I'm ready to describe what is the class of states for which currently we can construct a dual geometry. Okay? This class of states is what was called the graviton gas in some, by now, very old results by Jan de Boer. So the graviton gas is obtained in this way. So supposed to start from some chiral primary operator OK, of conformal dimension K, and act on this chiral primary operator with any number of generators of the global symmetry algebra. Okay, so here the fact that I'm only using the global symmetry algebra is important. meaning that I can act, for example, with L-1, okay? But okay, I cannot act with L-2, L-3, or even more importantly, I cannot act with L-1/2, for example. So in this CFT, which is an orbifold CFT, I could also have consider fractional excitations, okay, so fractional modes. Of course, these states are states that are allowed, and they are supersymmetric, at least at the free orbifold point of the CFT. But in general, we don't know how to construct dual geometries for this general class of states. Okay? But if I only act with the global part of the symmetry algebra, which is, as I've written here, the part of the symmetry algebra which is generated by J0, L-1, and the supercurrents G-1/2, okay? Then we can construct in general the dual geometries. So the states which admit a semi-classical description in supergravity are some sorts of coherent states, okay, which are obtained in this way. So start from the vacuum, okay? Start from the vacuum, 0, and act with any number of times, any number of copies of these chiral primary and descendants of chiral primaries. Okay? So you can act, for example, with P1 copies of this elementary ingredient OK1 and 1 and 1 P1, and then P2 copies with some other number, some other chiral primary. Okay? Or descendant of chiral primary. And then you form this sort of coherent, let's say, superposition of these states by using some, in general, complex numbers, B1 and B2. So you have to think of this state as a sort of a coherent state. Okay? And you have to think of these continuous complex numbers B1 and B2 as the parameters that parameterize this coherent state. So if you take this object, okay, this coherent superposition of these descendants of chiral primaries, then you can associate a geometry. Okay? You can associate a geometry to this object. Now, let me just make one comment. So the fact that here there is this sum, so that you have to consider these coherent states, was emphasized by Skenderis and Taylor. Okay? But for many purposes, you can also, let's say, mentally forget that there is this sum. Okay? Because in the large n limit, when these numbers B square are large, of order of capital N, and capital N is very large, then you can easily see that these sums are actually very much peaked over some average values. Okay? And these average values on which these sums are peaked are determined by the parameter B themselves. So the precise relation is the one which is written here. So if you take B squared divided by K, where K is this, let's say, the dimension of the chiral primary, then this gives you, on average, the number of times on which you have acted on the vacuum with these elementary ingredients. Okay? So for many purposes, you can just forget that there is a sum and just think that this sum is peaked over its average value. And then you can think of this number B as the number that tells you how many times, how many copies of this operator O1, O2, etc. you have in your state. So the question, as I said, is how to construct, these states admit a gravitational description, and the question is how to construct this gravitational description. So this gravitational description is given in terms of this superstrata that have already been introduced, for example, in the talk by Daniel Meyerson. So Daniel has given a very complete, comprehensive introduction to this topic. So even here, I think I can be brief. Okay? I will just briefly remind you that in order to construct essentially this superstrata, you have to start first from the solution at linear order in B. Okay, so these states contain, of course, many powers of B, so they are not just linear objects in B. But consider the limit in which you just take, at first, you assume, for example, that P is small and just consider the linearized approximation in these numbers, B1, B2, and so on. So in this limit, the solution describes just the linear perturbation around the vacuum. And the vacuum, of course, is represented holographically by ADS3, global ADS3 times S3. So you just study linear perturbations around ADS3 times S3. This is fairly easy. And this gives you the solution, the gravity solution at linear order in B. Then the not so easy task is to extend this linear solution to an exact nonlinear solution, which is valid when for values of B that are actually not small but large. Okay, so we are interested in the regime in which this B square is of order n, so that this state contains a macroscopic number, let's say, of elementary excitations, and hence it's really described by a classical geometry, a semi-classical geometry. So in order to construct this nonlinear extension, well, you have to, okay, so you have to be clever with solving the supergravity equations. Okay, so as I said, Daniel has described how to do this. Here, I just want to emphasize one point. The point is that the solution of this equation is in general non-unique. So you given a linear solution, there are many nonlinear extensions. Okay? And so you have to fix this ambiguity, and the way in which this ambiguity is fixed is by imposing regularity. Okay? So we choose every time there is an ambiguity in the choice of the nonlinear extension, we choose, we fix this ambiguity by choosing the regular solution. It's not obvious, but it turns out that if you impose regularity, essentially this eliminates all ambiguities, and there is a unique solution that you can find. Okay, so the end result of this construction is that there are families of smooth and horizonless solutions, exact solutions of supergravity, that are parameterized by these parameters B1, B2, B3, etc. that I've introduced before. Okay? All these solutions have fixed values of the global charges. So for every value of B1, B2, and so on, you can keep the B1, B5, and P charges fixed. Okay. All these solutions are asymptotically ADS3 times S3, but in the interior, the ADS3 and DS3 are non-trivially mixed. Okay, so these solutions are a product of ADS3 times S3 only at the boundary, but of course in the interior they are a complicated, let's say, non-trivial warping of the mixing of these ADS3 and S3 parts. Okay, so these solutions can also be extended to asymptotically flat solution, by which I mean solutions that are asymptotically Minkowski space times S1. Okay, so this has also been done. Okay? And okay, so essentially now this is the state of the art. Okay, so thanks to the work of all these people, now essentially, okay, modulo some technical detail, I would say, but essentially now we can construct a supergravity solution for all these, for any state belonging to this graviton gas that I described before. So, as a concrete example, a simple and concrete example, I will mostly use this state here. So, this particular state is a state that uses only one elementary ingredient, which is obtained by starting from a chiral primary of dimension 1 and acting with an arbitrary number little n of Virasoro operator L-1. So you act n times with L-1 with the chiral primary O1. You weight this state with this coherent state parameter B. Okay, and then you take, as usual, the coherent state. So you take the P's power of this, and then you sum over P. So this family of states is parameterized since there is only one mode here. So the mode is L-1 to the n times O1. Since there is only one mode, this state is parameterized by only one complex parameter B. And as I said before, this complex parameter B can vary, or more precisely, B squared, can vary from 0. Okay, if B is 0, then the state is fairly trivial. It's just the vacuum. Okay, and the maximum value of B square is capital N. Okay, so as I said, the B square essentially tells you what is the number of times in which you are acting, the number of copies of this elementary constituent that you have on the vacuum. So, and so since you have an orbifold of order capital N, you can only have a maximum number of copies, which is capital N. Okay, so this B square can vary between 0 and capital N. The dual solution, the dual supergravity solution, depends on this parameter B. Okay? When B square is equal to 0, as I said, the solution is the vacuum. So you only have ADS3 times S3. So in this case, you don't have any ADS2 throat. This is the shallowest throat you can have. It's just a global ADS3 times S3. But as you make B square larger, and as you make B square to approach its maximum possible value, which is capital N, then the length of this throat becomes longer and longer. Okay, so and as B square approaches capital N, this geometry becomes closer and closer to the BTZ to the BTZ solution. So the regime which is more interesting for us, of course, is the regime in which B square is close to capital N, because this should describe states that are more and more typical, meaning closer and closer to the black hole. So this is, I think, review of this superstrata. Okay? Let me pause a second to see if there are questions. Okay.
If there are questions, everybody is muted at this point and they cannot unmute themselves. If there are questions, they can raise their hand.
Okay, good. Okay, I hope
I'm not seeing any questions which are raised. If anybody has questions, they can just raise their hand and then I will unmute them.
Okay, good. Okay, thank you. Okay, then finally, okay, this was mostly a review. Okay, so now finally I can talk about the holographic probes of these geometries. So let's start from the 3-point functions, which are the easiest. So as I said, you can consider on the CFT side 3-point functions where you have 2 heavy operators that create and destroy, let's say, this heavy state, and then 1 light probe. Holographically, this corresponds to just 1-point function on the geometry. Okay. So if we take for these light probes, for this light probe, we take a chiral primary operator. Okay, so the light operator for us will be one of these OK chiral primary operators that I've already introduced before. And holography associates to each one of these chiral primary operators a particular field on the gravity side. Okay? So the dual field, the field dual to OK, I will denote by phi k. Now, it's not always, it's not completely trivial to identify precisely what is the field phi k, especially if k grows, if the dimension grows. There are many possible mixings between both between single particle and multi-particle operators. So to identify precisely what is the field which is dual to a particular state is in general a complicated, not very easy problem. Okay, so this problem was first addressed by Kanischeider, Skenderis, and Taylor, and then also in a series of other papers by these people here. Okay. However, once you have identified this field, then it is very easy to extract the 1-point functions. You just take the field, expand it around infinity, okay, the asymptotic boundary, and the coefficient in this expansion is precisely the 1-point function that you're looking for. So another thing, something which is particular to this class of observable is that, as I already said before, these 3-point functions do not depend on the CFT moduli. So it is something that has been proved, that these 3-point functions are independent of the CFT moduli. which means that you can also compute this 3-point function directly at the free orbifold point of the CFT. So you have two independent ways of computing the same quantity. One which is extracted from, which is based on the supergravity solution, and one which is based on purely CFT computations done at the free orbifold point. And then once you have these two numbers, of course, you can compare them, okay, and see if they agree. Okay? So of course, okay, in all cases that we have considered, we have always found a perfect match. And so this, as I said, I think it's a strong indication that the geometries that we have constructed are really duals to these, are really the holographic duals to these CFT states. Okay. So what we learned from this, okay, first of all, we learned that states dual to microstates need to have non-trivial multiple moments. So if you expand these the supergravity fields describing these microstates, since generically these 3-point functions are non-vanishing, generically you expect to find non-zero values for these expansion, multiple moment expansion of these fields. Okay? So of course, in the naive black hole geometry, all these multiple moments would be zero. Okay? So this is already something that tells you that instead, if you want to describe a microstate rather than let's say the mixed state that describes the black hole, then you have to turn on these multiple moments. It's also true that in typical states, these multiple moments will be very small. Okay, so the more the state is typical, let's say, the smaller these multiple moments will be. Okay? Especially if you consider, let's say, multiple moments of operators of low dimension. Okay, but okay, so there will be small multiple moments, but you expect to find generically non-zero values for the multiple moments. Okay, so this is, I think, it's a useful, important qualitative property of these microstate geometries. Okay. Another thing that you learn from here is it's a very non-trivial check on the gravity construction. Okay. So, for example, in some cases, these 3-point functions turn out to depend non-linearly on these parameters B that characterize the state. Okay. So there are, for example, cases in which these 3-point functions are quadratic in the B's. Okay? And so these 3-point functions are sensitive also to the non-linear completion of your geometry. So if you have done the wrong non-linear completion of your geometry when in constructing these geometries, you wouldn't get this agreement. Okay? So the fact that you get agreement, it's a strong indication that the nonlinear completion based on requiring regularity is actually what really has to be done if you want to describe the state. Okay? So if you want, this is a CFT proof of the fact that the regularity condition has to be imposed at the level of the supergravity. Okay? Okay, so that's more or less all I wanted to say about the 3-point functions. And now let me come to the probably more interesting observable, which is this heavy, light 4-point function. So contrary to the 3-point function that I described before, this heavy, light 4-point function is not a protected quantity. Okay, even if all these operators that appear here are supersymmetric operators. In general, these 4-point functions, of course, they always depend on trivial on the CFT modular. So this is really a dynamical quantity. Okay? And so this really tells you something. It really tells you something which you cannot understand simply by looking at the free orbifold CFT. Okay? So how do you compute then this 4-point function at the strong coupling point of the CFT? Well, of course, you can compute it with, you can compute it with this holographic recipe. So consider again the field phi k, which is dual to the light operator OK. So OK is again a chiral primary operator, which is dual to some supergravity field. So this supergravity field will be described by some wave equation in the bulk. Okay? So For example, you can consider some field, which is the simplest example is to consider a field which is described by a minimally coupled scalar in the 6-dimensional geometry, for example. Okay? But you can, of course, also consider, and we have considered also more general wave equations. Okay? So you will have this wave equation now. And take this wave equation, and so take these these supergravity equations and linearize them around the your non-trivial microstate. So you have to solve this wave equation in the background of your microstate. So so to pick a unique solution of this wave equation, you have to impose some boundary conditions. Okay, you of course always impose that inside the bulk, the solution should be regular. So at rho goes to 0, which in my coordinates represent the bulk of the solution, you impose regularity. Okay? And at the boundary, you impose the boundary conditions that are written here. So you require that the solution has a non-normalizable term, okay, which represents the source for the operator O bar, okay, and which is given by a delta function centered at the point where you have decided to insert your operator O bar. Now, once you have fixed the condition in the bulk, and you have imposed this condition, this non-normalizable condition at the boundary, at this point you have a unique solution of your wave equation. So everything else is fixed. And in particular, you can now expand the solution that you have found and extract the normalizable piece, which is this one. So this normalizable piece now is a completely determined function of your CFT coordinates Z and Z bars, which are the coordinates at the boundary of ADS3. Okay? So this function, B of Z and Z bar, can be extracted from the solution of the wave equation by doing this procedure. According to the usual holographic dictionary, this normalizable piece represents the VEV of the operator O in the presence of a source for an operator O bar. So it's nothing but the two-point function computed in this heavy state. Okay? So this function B is what gives you the heavy light correlator. Okay? So that's the recipe that gives you, that allows you to compute these correlators. Of course, in principle, this recipe is very simple, but the solution of the wave equation can be very complicated because remember that these microstate geometries are as complicated geometries as you could, very in general complicated geometries. Okay? So you cannot always do this. Exactly. Okay? Now, a case in which you can do this exactly is, again, if you consider this family of states that I've introduced before. So this is, consider this state here, heavy state, and this is a member of the family that I've introduced before, but I've taken a further simplification. I've taken the number little n equal to 0. So remember that the number little n was the number in which the number that denotes the number of times by which I'm acting with L-1. Okay? If I take little n equals to 0, it means that there are no L-1s. So it means that this state is not a descendant, it's just a Carroll primary operator. Okay? So that's the simplest case you can consider. Since it is a Carroll primary operator, this corresponds to a state that actually doesn't carry any momentum. So it's not really a microstate of a 3-charged black hole, but this is a microstate of a 2-charged black hole. So it's a very simplified situation. Okay? However, in this situation, it turns out that you are able to solve the wave equation exactly. Okay? And you can solve the wave equation exactly for two reasons. One reason is that the geometry dual to this state turns out to be separable in a sense. So you can split. You can dimensionally reduce the 6-dimensional geometries on the S3 And what you find is a three-dimensional geometry that doesn't depend on the S3 coordinates anymore. Okay? So this doesn't happen all the time. So, okay, it happens only for some particular subclass of microstate geometries. Okay? And this subclass is a particularly, this class of geometry is a class of geometry for which this simplification happens. Okay? So at least you can reduce the problem from 6 to 3 dimensions. Now in 3 dimensions, you have a wave equation. And okay, this wave equation can still be complicated. Okay? And indeed, if you take n bigger than 1, the wave equation is still too complicated to be solved exactly. Okay? And this is the wave equation that has been solved with some WKB approximation in the series of paper that you have already heard of from the talk of Pierre. So these people here have managed to actually solve the problem approximately for n bigger than 1. Okay? But okay, if you just want an exact solution, however, okay, this can only be obtained if you take little n equal to 0. Okay, and this is what we did. Okay? And the result of this exact solution is the correlator that I write here. So as you can see, the correlator is still not super simple. Okay, in particular, in general, we were not able to perform in closed form all these sums here, so this series. Okay, so that's the best thing we can do. We can represent the correlator in terms of this series. Okay, but I will show you later that even this series representation could still be useful to understand many important qualitative properties of these correlators. Okay. So before I continue, let me just clarify the notation. So this correlator, of course, depends on the coordinates z and z bar, which are the coordinates on which we have inserted one of the light operators. Okay, let me just remind you that we have a heavy operator inserted at infinity, another heavy operator inserted at 0, then one light operator you can insert at any point, finite point you want, for example, 1, and then you're only left with one, let's say, free cross ratio, which is this z and z bar. Okay, so z and z bar parameterizes the position of this light operator, okay? And tau and sigma are another parameterization of z and z bar. Tau and sigma are the so z and z bar are the coordinates on the plane. Tau and sigma are the coordinates on the cylinder, okay, the boundary cylinder. Okay. And another notation that I want to clarify is this parameter alpha. So we said that we already said that these geometries depend on one parameter b. Okay? And okay, we trade this parameter b by this parameter alpha. Okay, so in this way. So this alpha is also varies between 0 and 1. The easy limit is the limit in which alpha is equal to 1, because that corresponds to the limit b equal to 0. That's just ADS3 times S3. Okay? And indeed, you can check that if you set alpha equals to 1, this correlator dramatically simplifies and just becomes just the correlator of two operators in the vacuum. Okay, so it's the simplest correlator you can have. So of course the interesting case is to keep b different than 0, and in particular the interesting limit is the limit in which alpha goes to 0, which is the limit in which you get closer and closer to the BTZ black hole. So now let me discuss some properties of this holographic result. Okay. Okay, so one first limit that you can consider is, for example, this light cone limit. Okay? So that's the limit in which you take the variable z bar and you send it to 1, okay? While keeping this variable z fixed. Okay, so of course, in order to take this limit, you actually have to continue from the Euclidean patch to the Lorentzian patch, okay? Because otherwise z and z bar in the Euclidean patch or the complex conjugate of each other. Okay, but there is no problem in doing this. And so you can consider this light cone limit. And in this light cone limit, since z bar goes to 1, the only operators that contribute to this limit, the operators that dominate in this limit, are the operators that have conformal dimension equal to 0. Okay, so of course, okay, so let me go back. Sorry, maybe 1 second here. Okay, so when z goes to 1, you can consider the OPE between the light operators O and O bar. Okay? In this OPE, in principle, there are many operators that are exchanged, but in the limit in which z bar goes to 1, the exchanged operators that dominate are, of course, the operators with the lowest possible conformal dimension h bar, and the lowest possible conformal dimension h bar is h bar equal to 0. So operators with h bar equal to 0 are just the conserved charges of your theory. And the conserved charges of your theory are the Virasoro charge, of course, and the Virasoro generators, and the generators with the R symmetry. Okay. So in this limit, you expect the correlator to be dominated, so to be the contribution of this correlator to be just given by taking the identity and acting on the identity with the Virasoro and the R symmetry descendants. So you can construct what is called the affine conformal block of the identity, which is obtained exactly in this way, by resumming the contributions of the identity and all the descendants of the identity. This was obtained in a nice series of papers by these people here, Fitzpatrick, Kaplan, and Walters. Okay? And this is what you obtained if you resum all these contributions. Okay, so it's what is called, as I said, the affine block of the identity. This is the result that you get in the limit of large central charge, of course. Okay, because for finite central charge, the purpose, I mean, resumming all these operators is actually very complicated, and there is no closed expression which is known. Okay? But if you are in the limit of large central charge, you have a closed form expression, which is this one. Now you can take our supergravity result in the same limit. So the limit z bar goes to 1 in cylindrical coordinates means the limit in which sigma goes to tau. In this limit, you can easily see that the series given the correlator, so the series here over L and N, is dominated by the terms where L is much bigger than N. Okay, so these are the terms that dominate this series when sigma is approximately equal to tau. And then in this limit, then you can perform the series. Okay, so the series can be computed, and if you compute the series, you find precisely this result. Okay? So this is a check. Okay, it's a I think a non-trivial check on the supergravity computation, and it tells you that at least the contribution given what is called sometimes the universal contribution to the correlator. Universal because it's just given by the conserved charges of your theory. So the universal contribution of this correlator is exactly what is expected by the symmetries. Now, another interesting limit to consider is the limit in which you take this parameter B and you take it as small as possible. Okay, small but not 0, because I said if you take it 0, you just find the vacuum, which is not very interesting. Okay, but you can consider the limit in which you take B square and you send it equal to 1. Now, in principle, this limit is outside our approximation, because the approximation in which the supergravity description is supposed to be valid is always the approximation in which B square is a macroscopic number. Okay, you don't expect to trust the solution, the supergravity solution, when B square is of order 1. Okay, so however, formally you can still try, okay, to take this limit and see what you get. Okay? So in this limit, the heavy operator actually becomes a light operator, because if B square is equal to 1, it means that you are not acting with many copies of O1 on the vacuum. You're just acting with one copy, okay? Because remember that B square was the number of copies of your chiral primary operator. Now you have your heavy state that in this limit just becomes an ordinary single particle operator, O1. And your correlator, which is the heavy, light correlator, in this limit becomes a correlator with only light operators, okay? OH has been replaced by O1. So the first non-trivial contribution to this correlator is a contribution of order B square. Okay? B square because you have two heavy operators, so you have 2 times B, which is which gives you B square. So, and you can see what you get in this limit. Okay? So if you take this limit on the supergravity result that I showed you, okay, then in this limit again, it is possible to perform all these horrible sums that I showed you before. And all these horrible sums that I showed you before can be rewritten in terms of the standard D functions that give the Witten's contact diagrams. Okay, so these are functions that are very common and very familiar to people that have been performing these holographic computations using Witten diagrams techniques. Okay? So precisely the same D functions appear in the B square going to 1 limit of our correlators. Okay? And you can check that indeed in this limit you find precisely a correlator that has exactly the right properties to be interpreted as a light correlator. So this means that even if it's not obvious from our computation, the limit B square small is actually smooth, and you can also extract light correlators from this holographic computation performed in this microstate geometry. Okay? So indeed, we have generalized this computation. Right? The computation at order B square can be done for a very generic microstate now. So since you don't have to solve the wave equation exactly in B, okay, at order B square, you are able to solve the wave equation actually in a much more general case of superstrata. Okay? And in a series of papers with these people here, Rodolfo, Sasha Tyukov, who is a postdoc in Padova now, and Zonkao Wen, who is a researcher at Queen Mary. So in a series of papers, we've used this method to actually compute the general class of 4-point single particle correlators between 4 chiral primary operators of this D1, D5 CFT. Okay? So a whole class of correlators that was not known before. Okay? So this is not directly related with black hole microstates, but I think it's an interesting, let's say, byproduct of this microstate geometry. So if you know these microstate geometries, you can also compute these correlators. Okay? Now, coming back to issues that are more relevant for the black hole problem, okay, let me consider examine the late time behavior of the correlator that's computed. And in order to do this, I will focus on the regime which is more interesting for the black hole, which is the regime where this parameter alpha, as I said, becomes very small, which is equivalent to say that the parameter B square becomes very large, and your microstate geometry develops a very long froth and becomes almost indistinguishable from the BTZ solution. So as I said, since we are considering 2 charge geometries rather than 3 charge geometries, when I'm talking about BTZ geometry, I'm actually meaning the massless limit of the BTZ geometry, right? So, which is a geometry that doesn't really have a finite horizon, but it just has a singularity, okay, rather than a horizon. So anyway, you can still consider this massless BTZ geometry, and you can still compare the behavior of the correlator that we've computed in the microstate with the behavior of the correlator that you would have computed in this massless BTZ geometry. So in the limit in which alpha goes to 0, again, we are able to approximately compute the correlator. Okay, so the series again can be resummed because it's dominated by the terms with n large these times. Okay? And what you get is this result here. So this result has a oscillatory part, okay, which okay is not okay. The only interesting part about this oscillatory part is that it's just an oscillatory function of sigma and tau. Okay? And then there is one part which is written here in orange, okay, which is the interesting part of the correlator. So this part of the correlator is interesting because, as you can see, if you consider times which are large, okay, so if you take tau, which is the time, Lorentzian time, which is large, but not very large. So in particular, if tau is much smaller than alpha to the -1. Okay? So remember that alpha in our limit is a large number, so tau can still be large, okay, but still be smaller than alpha to the -1. Then this quantity here, alpha times tau, is very small. Okay? And then you can expand this exponential in Taylor series, okay? And then you find that the Taylor series expansion of this quantity here just gives you, okay, a denominator a factor of tau. Okay? So you will find that your correlator in this regime of large but not so large time decays like 1/tau. So this decay like 1/tau is precisely the decay that you find if you compute the 4-point correlator in the massless BTC geometry. So if you had considered the ordinary BTC geometry, you would have found an exponentially decaying behavior. Okay, but here we find only a power law behavior, as people were also saying yesterday. We only find the power law behavior because we have 2 charge rather than 3 charge. Okay. So sorry, Nick, would you like to say something? Yeah.
Sorry, it just popped up. I was saying we're coming up on the hour since you started.
Yeah.
So, you know, we don't mind extending by 5-10 minutes, no big deal. But our sort of rigid deadline is, you know, 4-ish.
I will take probably 5, at most 10 minutes to just talk about.
That's perfect.
Okay. Thank you. Okay, so this is okay. So this is, as I said, the BTC regime. But what is important is that for every microstate, every microstate has an alpha which is not precisely 0. So alpha can be small, but it's not precisely 0. Okay? So, and if you look at this microstate with small but non-zero alpha for large enough time, so if you consider times which are bigger than alpha to the -1, then this approximation 1/tau is not appropriate anymore. And you find that this, so you have to keep the whole exact expression, and you find something which doesn't decays anymore, but simply oscillates with tau. Okay? So this is precisely the behavior that you expect in a unitary theory. Okay, so the correlators in a pure orthogonal state in a unitary theory finite entropy should not vanish at large times. Okay. And that's precisely what happens in our microstate correlator. Okay, so this was vanishing at late times for the correlators computed in the black hole was a puzzle that has been emphasized many years ago by Juan Maldacena. Okay? And we find that in this using these microstates, okay, you evade this puzzle. Okay? So the late time behavior of the heavy light correlators is consistent with unitarity, already a large C, because we only use in large C results. So it's supergravity, so large C results. So we don't need to include any 1/C corrections in order to obtain this consistent behavior. Now, very briefly, I will try to summarize in a few minutes what you can do also in the Regge limit. So as I said, in many cases, solving the wave equation exactly is not very doable thing to do. Okay, so you can ask if there is a limit in which things simplify but still are non-trivial, and one such limit is the Regge limit. So on the CFT side, the Regge limit is defined as a particular kinematical configuration of your let's say 4-point correlators. And it's a kinematical configuration that is obtained by starting from the Euclidean correlators and doing an analytic continuation of this Euclidean correlator by sending, let's say, sending Z around the origin once. Okay, so this is a non-trivial operation in general because these correlators have branch cuts. So when you do this analytic continuation, you pick up generically branch cuts of these correlators. So, and then after you've done this analytic continuation, you take Z and Z1 and send it to 1. Okay? So this is what defines the Regge limit on the CFT side. The bulk dual of this operation is, is described in this way. If you consider light operators, light correlators, this was understood already years ago by Cornalba and Costa, Penedones, and Schiappa. Okay, so this corresponds to have this corresponds to having two particles scattering at high energies and fixed impulse parameter. Okay, so this regime is a high energy regime. Okay, the regime which is well described by this aconal approximation. Okay. Now, the same regime has been considered more recently by these people here, okay, for the heavy light correlators. Okay. In this case, you don't have two particles colliding. You have just one heavy background, okay, represented by the heavy operator, and you have one particle scattering off this heavy background. Okay. So this is the high energy limit of this light probe that interacts with this heavy background. So this limit is described then by a null geodesic, null because at high energy the geodesic is approximately null. So this limit is described by a null geodesic that propagates in the microstate geometry. So that's precisely the problem that was considered yesterday by Francisco. Okay? So if you take an geodesic in this, the starts and end from the boundary, okay, with fixed momenta, p tau and p sigma, okay, you can compute the phase shift. The phase shift, which is defined like this. So take the product of the momenta times the shift time and angular shift that you find for your geodesics at the boundary. So this is something that you can compute on the bulk side for any microstate geometry. Okay. Let me also emphasize that if you try to do this computation for the BTZ solution, you wouldn't be able to extract any phase shift, because in that case the geodesic just falls into the horizon and never comes back. So for the BTZ geometry, you cannot define any phase shift, but for any microstate different from the BTZ, this phase shift is always defined and it's always finite. Okay. So how is this phase shift related with the CFT? So what does exactly this phase shift computes on the CFT side? Okay. So to understand this, consider the limit of the correlator in which Z goes to 0. And in my convention, Z goes to 0 means that one of the light operators collides with the heavy operator. So in this OPE limit, the states which are exchanged are just the multi-particle states obtained by taking, let's say, one heavy operator and one light operator. And then you can also add some derivatives here. Okay. So this is a whole series of multi-particle states that are the states that contribute to these 4-point correlators in the limit Z goes to 0. So these multi-particle operators have a naive dimension, which is just the sum of the dimension of the heavy operator, or the light operator, plus the dimensions due to these derivatives here, 2n plus L, plus an anomalous correction. So an anomalous dimension, which of course is in general non-zero once you go away from the free theory. So what's the interpretation of this dimension from the bulk point of view? It's a simple interpretation. These dimensions are nothing but the energy levels of the bound states on top of the microstates. So you consider non-BTS excitations on top of the microstates. If you consider the bound state energy levels of these excitations, these are precisely these dimensions here. Okay. So these dimensions can also be expanded around ADS3. Okay, so we parameterize this expansion with this parameter mu. Mu goes to 0 means ADS3, and mu small means an expansion around ADS3. Okay. And in the same way, you can expand the phase shift around ADS3. And the precise relation between the objects that you extract from the geodesic, so the phase shift, and the CFT, sorry again. So the precise relation is given here. So the phase shift is precisely equal to the limit of large N and L of these anomalous dimensions. Okay. So this is some recipe that has been understood already, okay, in previous papers that precisely connects quantities computed from the geodesic and quantities of the CFT quantities. So as a first application, we have done this for the following geometry. So we have considered on one side a conical defect geometry, which is this one. And on the other side, we have considered our favorite microstate. Okay, so the microstate that I've been talking about until now. So the microstate with k equals to 1 and n equals to 0. Okay. So these, if you can compute, of course, the heavy, light correlators in both these geometries. Okay. You can find that in the light cone limit, these two correlators are exactly the same, meaning that if you just look at the universal contribution to these correlators, there is no difference between the two. Okay? But the two geometries are actually different, and the two correlators are different. Okay, and this difference is apparent also in the Regge limit. So the phase shift and the anomalous dimensions are different. In both cases, you can check that delta and gamma satisfy the relation that I showed you before. Okay, so even this is a further check on, let's say, this microstate because it gives you the expected gamma. Okay, and something that I also want to emphasize is that also both these correlators, both the correlator computed in the conical defect and the one computed in the microstate, satisfy non-trivial bootstrap constraints. So here I don't have much time to explain this in detail, but you can compare the limit z goes to 0 and z goes to 1 of the correlators, and you can check that in both cases these limits are consistent. Okay? So we seem to have two different correlators, okay, that are identical at the level of the universal sector of the theory, okay, but that are otherwise different, and they're both consistent. They seem to satisfy all consistency requirements implied by the CFT. However, we know that this conical defect is in general not a pure state, because if you take this conical defect alpha, okay, parameter alpha, and you take it generic, okay, this doesn't correspond to any pure state of the CFT. It's a pure state only for very particular values of alpha, only if alpha is 1 over an integer. For generic values of alpha, this is not a state of the theory. So I think it would be interesting to understand how to tell, just based on consistency of the CFT, that this geometry, for example, is not an allowed pure geometry. Okay, so this I leave it as an open question. Okay, so I'm essentially done. I just have to wrap up. Okay, so probably sorry, I went a bit late, but okay. Let me just briefly mention that we know how to construct supergravity geometries for a large class of microstates. Okay. And let me also mention that this construction is consistent with unitarity. Okay? And the examples that we know then provide a string motivated mechanism to have non-trivial structure at the horizon. Now, these open problems, okay, the classical supergravity works well for atypical states. And the biggest open problem is how much of our analysis can be extended to typical states and also to non-BPS states. So it is possible that the fastball paradigm actually will not work if you just restrict to supergravity. It is possible that you might have to consider more, let's say, generic, either stringy or quantum settings. Okay. And the question is, do we have quantitative tools to describe these microstates beyond supergravity? Now, the hope of this program is that maybe using CFT and using general consistency properties of the CFT, like bootstrap, unitarity, Lorentzian inversion formula, and so on, the hope is that maybe this can give us some hints and clues of what is the structure of the solutions described in the microstates at the horizon scale. Okay, so I'm finished. Okay, sorry again if I went a little late. So.
Thanks a lot. I now unmuted. I mean, now all the participants are muted, but now they can unmute themselves, so people can actually ask questions.
We have time for about 5 minutes, and then we should. So, any quick questions or?
Yeah, can I ask a question?
Andrea.
Good.
Well, very interesting talk. Thank you. I was just wondering if you had the chance to decompose your correlator into corresponding conformal blocks. No, if you know what exactly is running in the channel where you fuse the light operators and the heavy operators together. So it's clear that there is a vacuum Virasoro block. And then one would expect double trace operators made out of the light scalars to contribute.
Precisely.
So,
yes.
So I was just wondering if you could fix the OP coefficients of these guys.
Okay. Can you hear me?
Yes.
Yeah.
And we can see your slides also, your whole screen.
Okay, good. Okay, then yes, we did precisely what you're asking. Okay, and this will appear when we write the talk. So the point is that, for example, okay, both for the conical defect correlator and also for the correlator in the microstate. So apart from the contributions of the block of the identity, which is a universal and of course has to be there, okay, we find that there are also other contributions that are precisely representing these multi-particle states that you are describing. Okay, and actually these multi-particle contributions are essential and necessary to have consistency with the bootstrap. So if you don't have these contributions in the, let's say, Z goes to one channel, then you would be inconsistent with what you find in the other channel. Okay, so we precisely did this, and we could also essentially match pretty precisely, I mean, including all numerical coefficients, all the 3-point functions and the anomalous dimensions that you can compute, for example, from the Regge limit with the one that you can extract directly by doing the direct Euclidean, let's say, OPE of these correlators, and everything matches precisely. Yeah.
So what you say is that in case 1 and case 2 you have different contributions due to this.
Exactly, different contributions. So they're still multi-particle states. Okay, apart from the contribution of the universal contribution, which is the same because it's just determined by this parameter alpha essentially. And if you compare solutions with the same alpha, the universal contributions are precisely the same. But there are different ways, let's say, to extend this universal contribution to give you something that looks like a consistent correlator. So, as I said, it would be very interesting to understand if there is maybe some consistency requirement that we are forgetting and that allows you to distinguish, let's say, to understand why 2 is a real microstate and 1 is not, for example.
Yeah, it would be interesting. I'm really looking forward to your paper. I'm curious to see how the double trace operators influence the anomalous dimensions in the cross channel.
Okay, yeah, of course, we were very much inspired by all your recent papers in doing this. So, of course, we can certainly try to discuss.
Yeah, thank you.
Stefano, I noticed that in your, you made to relate the phase delay from the geodesic to the anomalous dimension, you made an expansion, but that was around about a shallow geometry, wasn't it? It was, you know,
yes, that's an expansion around the shallow geometry. Okay, so this.
So what happens when it gets deep?
Yeah. Okay. So the answer is that we haven't looked at that very much. Okay. Okay, I think it's still don't know exactly what happens to this relation here, for example, when you go away from this perturbative regime. Okay. So I think Andrei might have something to say about this, because I think they also observed that this relation already, if you go from the first order to the second order, becomes less trivial. Okay, but I think the answer is that I don't know if anyone knows what is the precise relation between the delta and the gamma away from this perturbative region.
I guess I'm just trying to ask, if you have a very deep geometry, you can easily, in general, in supergravity, calculate these phase delays and things like that. What are they going to tell you about the state of the conformal field theory? I mean, this is nice, but this is absolutely perturbatively around the vacuum.
Yeah. Okay, I completely agree with you. Okay, and
No, it's not a criticism. I want to know what you're going to learn from these delays.
And in particular, can you use Andrei's methods to actually compute stuff in deep microstates?
Yeah.
With geodesics.
Yeah. Okay. So what I can say about this for the moment, which is a bit preliminary, is that first this phase shift can be computed exactly in for any microstate. Okay, so you don't need to do this perturbative expansion in order to compute the deltas. Okay. Now, if you are asking me what is the precise relation between the deltas and the CFT, okay, away from this perturbative regime, I think the answer is, for the moment, I don't know exactly. Okay, and it will certainly, so it certainly will have to do with, again, with these bound state energy levels and so on and so forth. Okay. But if you're asking me precisely how, what is the relation with the CFT, I think at the moment I still don't know. Okay? So I believe that even for deep microstates, there will be something to extract from this delta, I mean, for sure, and that not only there will be something to extract, but also you will be able to, for example, say if this delta satisfies some consistency requirements, things like that, which is what is more interesting for us, right? So we really want to understand in which way the microstates, let's say, are consistent with unitarity and things like that. Okay. So, for example, having just the BTZ, okay, so having the BTZ solution where the delta is, if you want, infinite, it cannot be even computed. I think that would be immediately inconsistent with the CFT, because I think the CFT will certainly predict that this delta is finite. Okay, so that, I mean, the first the first very superficial, let's say, conclusion is that looking at these phase shifts, I mean, rules out the BTZ as an allowed good, let's say.
So to be provocative, is this a proof that therefore microstates can't have horizons?
Yeah, I think you could argue towards that.
I'm sure we'll come back. Let's defer that discussion to later this afternoon.
I think Juan Madasana has a question also. He's raising his hand.
Oh, sorry. Go ahead.
I have a question, comment. So you were talking about the conical defects, right?
Yes.
And
yes.
if I'm not mistaken, you were talking about the supersymmetric case, right? These are supersymmetric.
Yes.
Yeah, so then I think these conical defects have also some structure on the sphere related by supersymmetry to this alpha.
Exactly. Yes, that I didn't write here. I only wrote. Yeah.
So yes. But once you consider that structure and the full geometry for integer values, you have an AN singularity or AK singularity. But for non-integer values, you have some object which is inconsistent when you look at it even from outside the object. So there is a vibration. So the AK singularity is a bit like a Kaluza-Klein monopole, right? Yeah. And it involves a circle. So when you look at the space around the singularity, there's a circle fibered over a sphere, right? Over, I think it's a two-sphere. And the magnetic field is an integer for integer k. But when k is not an integer, it's that's not an integer, so it's an inconsistent solution even outside of a singularity.
Yeah, I perfectly agree with this. I mean, I perfectly agree that from the point of view of the supergravity solution, it is easy to see that alpha non-integer is not an allowed. Is not, even from the supergravity point of view, is not an allowed.
Okay. Yes, that's right.
Our puzzle was, okay, suppose that I give you this correlator. So I can extract from this geometry, I can extract using this holographic precision that I showed you before. I can extract a correlator, which I could even write down. I didn't write it down, but okay, I could write it down, okay, explicitly. So that's some sort of 4-point function. Apparently, that correlator, purely from the CFT point of view, doesn't violate any basic principle.
Presumably might violate something if you include modes that have angular momentum on the sphere, because the problem comes from things that have they're moving on this circle or
okay, yeah, okay,
magnetic field, and then since that's inconsistent, that those correlators might have some trouble.
Yeah, that might be an interesting observation. Okay, I have to say that we have, let's say, computed correlators with 2 different types of light operators in these conical defect geometries. One light operator has no R charge, so it's really just a minimally coupled scalar with no R charge. So you would expect that, okay, that correlator is not sensitive to what happens on the sphere, and so probably if there is some inconsistency, you wouldn't see the inconsistency of the type that you are referring to. But we've also computed, consider a light operator that has a non-trivial R charge. Okay? So some correlator that should also be sensitive to the structure of the S3. And okay, we don't find any obvious inconsistency also for that correlator, but okay. We'll certainly try to. Yeah.
We should probably wrap it up. Let's perhaps just take a 5-minute break, and we started 10 minutes late, so let's start with Jan in about 8 minutes at 16:10. Does that sound good, Joseph?
Yep, sounds good.
Okay, so we'll resume with Jan at 16:10. We'll leave the link open. You can talk amongst yourselves, but
it all goes on. It actually maybe not, because it's everything is recorded on YouTube. We'll not do another YouTube.
Yeah. Well, okay.
So maybe it's better to keep discussions.
Well, no, people can talk. Just remember, you're going to be very public in your conversation.
How do I stop sharing the screen? Now I got a bit lost.
Well, anyway, thank you. It was very nice talking.
I just stopped it myself.
Okay, thank you.
Jan, if you're there, yes, you are there. Do you want to start sharing your screen and getting the title page up?
Sure.
Thank you. We'll start in a couple of minutes.
It's visible.
Yep. You can see everything. It looks great.
Wow, you have many affiliations. Looks like Grappa.
I saw in some other fields that they always put all these logos on everything. So.
Yeah. Wow.
Reminds me of French movies usually, which put like 1,500 different sponsors. So I think we'll do again like in the previous seminar. We'll have everybody muted by default, and then if people have a question, they can raise their hand on the side panel, and then I'll give them the microphone. I'll interrupt whenever needed.
I heard some pinging. I don't know whether that means
It's
somebody's.
my Zoom. It's my WhatsApp.
Okay. How do we see whether somebody's raised their hand? Do we just keep the
You see
participants?
it on the right. There's on the right panel. There is when you look at participants.
Ah, good. Then it'll come to the top of the list.
Yeah, they pop to the top of the list. Yes.
Good. Okay. Excellent. We'll go back to less militant forms of the meeting tomorrow, but today there's an enhanced chance of being Zoom bombed.
Yep. I think the YouTube is functioning, so
Okay.
the streaming on YouTube goes on. So
Okay, I think it's 16:10, so let's make a start. So this afternoon, the second talk, very glad to have Jan de Boer, who's going to be talking about gravity and randomness. So please go ahead. Yeah.
All right, thanks. Yeah, it's a great pleasure to be sort of in Saclay right now. I'm going to talk about, thanks for the invitation. It would have been so much nicer to meet in person. I'm kind of getting sick and tired of these virtual meetings, to be honest, but anyway.
Let me just say that we're going to do this again next year, but in person in Paris.
Then we get to sample your wine cellar.
Indeed.
Right, so in this talk will be about gravity and randomness, and I will explain the meaning of the title will become clear as we go along, and this is based on some joint work with Alex Bellin, which should appear on the archive tomorrow. So one question, and one key question that underlies maybe some of these discussions about gravity is how much knowledge does gravity have about the high energy features of a theory? How much access do we have to that information? Can we resolve all the individual high energy states? If not, how much information is accessible in gravity about the high energy part of the spectrum? Now, gravity is a low energy effective field theory. So you would normally think that gravity has no access to or possesses any information about energies that are above the cutoff. That could be the Planck length, it could be some other effective scale in the theory. But you would think that gravity knows nothing about anything above those length scales. But we know something, because just the mere existence of a consistent UV completion does impose a whole bunch of constraints on low energy effective field theory. We don't know what they are. We know some, and the whole program to figure out what they are goes under the name, I guess, of the Swampland program, which is trying to figure out which low energy effective field theories are UV completable and which ones are not. So definitely there is some information available from this point of view. You could say that the information paradox in some sense is also about some apparent tension between the validity of low energy effective field theory and the existence of a consistent unitary UV completion. Now it's interesting that I'm sure you've heard talks or read papers that the Page curve, which is a consequence of unitarity, which is the curve that tells you how much entropy is in Hawking radiation as a black hole evaporates, was recently shown to be obtainable from gravity once you include Euclidean wormholes in various computations. Now, that does not tell you that you actually have access to all the details of the Hawking radiation, but this important feature of Hawking radiation, namely that the entropy goes up and then the entropy goes down, is apparently something that gravity knows about, at least to the extent that these computations are reliable, and there's some other issues about them perhaps. But gravity appears to know about the fact that the theory is unitary if you include wormholes, and that suggests that non-perturbative Euclidean gravity has some access to this feature of the high energy spectrum. It has some access to high energy information. But again, this is still kind of coarse-grained information. You know about unitarity, you know about the entropy, but it's not clear that you know about all the microscopic details of the Hawking radiation. So it's still not entirely clear from this point of view how much gravity knows or does not know about the high energy part of the spectrum. So I've heard many talks about microstates. So I don't want to get into a long discussion about definitions, but one version of what you could call the microstate program is that it's a program is aimed at finding the largest possible classical phase space of smooth horizontal solutions of the gravitational field equations. You could argue whether you need stringy sources in it or not and things like that, but this is a rough version of the microstate program. And it would certainly be remarkable if the quantization of this phase space, because we're looking at a classical system, so what we find is a classical phase space. To figure out what the quantum degrees of freedom are, we would need to quantize the phase space, we would need to compute its symplectic form, etc. But it would be remarkable if you could find a large family of smooth horizontal solutions to the gravitational field equation that would have the property that if we would quantize that phase space, we would get an entropy that's of the order of the black hole entropy. Because that would mean that you would be able to detect essentially individual microstates already at the gravitational level. And that would also imply that gravity would have complete access to high energy information in a sense. Now, first of all, this might lead to some tension with various intuitions that might have from statistical mechanics and hydrodynamics. Because, for example, in hydrodynamics, it's impossible to recover the entire phase space of all the molecules by just looking at very detailed hydrodynamical configurations. And if you believe that gravity, in some sense, emerges from these high energy degrees of freedom in a version of a hydrodynamical limit, then in hydrodynamics it does not work, so why would it work in the gravitational case? You would also need to investigate whether, if you have this big phase space, whether, well, a typical single degree of freedom is associated to a Planck size cell on phase space, because the number of degrees of freedom is roughly given by the volume of the phase space in Planck units. And you need to wonder if you localize a wave packet on a Planck size cell in phase space, whether you're still within the validity of effective field theory. And if there were that many degrees of freedom, it's possible that one would get some sort of space-time foam version of the degrees of freedom, and it would certainly be interesting to understand all of this in more detail. But there are certainly issues that one has to worry about. Now we have seen many examples of actual microstates. I think the current status is that if you look at supersymmetric cases, where we are in a regime of parameters where there is a large supersymmetric black hole in the bulk, then once one quantizes the corresponding phase spaces of classical smooth horizonless configurations that have the same quantum numbers at infinity as the large supersymmetric black hole, that we can achieve a number of degrees of freedom that grows with some power of the entropy, but the power for the time being appears to be less than 1 for large supersymmetric black holes. For small supersymmetric black holes, one can achieve alpha equals 1. The situation for non-supersymmetric black holes is much less clear. It's actually very hard to find reliable, stable microstates for, say, for a generic Schwarzschild black hole. So in this talk, I want to try to say something slightly more quantitative about the information, the high energy information that gravity has and has not access to. And in particular, I want to propose that gravity, keep in mind the timing, gravity has only access to certain statistical properties of high energy states. And I would also like to explain how one can use this point of view to potentially improve our understandings about the appearance of and the role of Euclidean wormholes and the role that they play in gravity. The statement that gravity has only access to certain statistical properties of high energy states and not to more fine-grained information of high energy states is inspired by, in particular, by the eigenvalue thermalization hypothesis. It's also inspired by an infinite series of historical work, essentially, because we have seen many examples where gravity knows about some statistical features of the high energy spectrum. For example, we know examples where the spectrum is given by a random matrix theory to a good approximation, and like some moments of these random matrix distributions are accessible in gravity, but the actual individual level spacings are not. And in some sense, the eigenvalue thermalization hypothesis expresses this statement. I've written the eigenvalue thermalization hypothesis here. So it's the statement that in a chaotic quantum many-body system, or maybe a chaotic quantum field theory, that if you have a simple operator O alpha, this should be an A, sorry, a simple operator OA, and you look at its one-point function between two exact energy eigenstates, then there are two terms on the right-hand side. The first term here is a diagonal term, delta ij, that multiplies a smooth function of the energy. And obviously the energies are equal because I is equals to j here. And then there's a second term that involves a factor with the entropy associated to the average energy of the two states. There is a function that smoothly and slowly varies with the two energies, with the average energy E bar and the difference in energies delta E. And then here there is essentially a Gaussian random variable. So what this expression accomplishes is that it first of all guarantees that if you take a typical pure state in the theory, you can think of it maybe microcanonically. So take a typical pure state, which is some random superposition of energy eigenstates sampled from a narrow energy window. And what this will do for you is that if you compute the one-point function in O alpha in a typical state, is that the first term will basically just spit out Fa of E, the energy associated to this microcanonical energy window. And the second term essentially goes to 0 because of the random matrix, whose expectation value is 0. And that then tells you, so this formula guarantees that if you take a typical state, that a one-point function of a simple operator is exactly equal to the thermal expectation value of the same simple operator. So in order to reproduce this feature of finite temperature physics and of thermodynamics, this first term does precisely the job. You can ask, what's the purpose of the second term? Well, clearly, the first term cannot be an exact statement. That would be too much of a good thing. The purpose of the second term is essentially to get the two-point functions of simple operators to come out correctly. What you can do is, if you take this expression, you can take a two-point function of simple operators O between typical states. You can insert a complete set of states in the intermediate channel. And if you do that, you will then find that the two-point function of simple operators, they can be separated in time. In a typical state, we'll again agree with the thermal value answer, and that thermal answer is related to a suitable combination of the functions f and g that appear in the eigenvalue thermalization hypothesis. So it is in some sense a way to elegantly repackage the information about 1 and 2 point functions in thermal states, and to guarantee that if you take a typical state, it to great accuracy reproduces the thermal answer. Right. And this is the statement that these are Gaussian random variables. The expectation value 0 and the variance is equal to 1. Now, in an interesting recent paper, Pollack, Rosali, Sully, and Wakeham a few months ago used the eigenvalue thermalization hypothesis together with very precise microcanonical Haar averages over the unitary group to compute products of 1 point functions in sort of just products of 1 point functions. So it looks like it's not the expectation value of the product of operators is the product of expectation values of operators. And they investigated products of 1 point functions in this context. And then because of all the randomness that is in ETH, if you then do some precise Haar averaging of the unitary group to sort of do an average over all microcanonical states, over all typical states, then besides producing the obvious thermal answers that you think should be there, there were a few new contributions that came out from the averaging procedure. And some of the structures that came out were reminiscent of wormholes at a sort of cartoon level. Unfortunately, this did not seem to agree to any immediate obvious gravitational computation because it was a bit done at the level of a time model. But the spirit of this proposal is very much in the spirit of what I will be talking about now, except that our picture will be somewhat different from what they were proposing. Now, for the remainder, I will restrict to conformal field theories, and at some point I will mostly be talking about two-dimensional conformal field theories. But it will be mostly about conformal field theories. Now recall that conformal field theories are completely described in terms of the spectrum of scaling dimensions delta I, or energies, if you take the point of view of quantizing the theory on the cylinder, plus operator product expansion coefficient Cij(k). And especially in large N theories and large conformal, large central charge theories and the type of conformal field theories that we use in holography, there's typically a distinction between what we often call light operators and heavy operators. Light operators are typically operators with dimensions of order unity. Heavy operators have dimensions that scale typically as n squared or the central charge or something like that. And I will distinguish light operators with labels A and B and so on, and heavy operators with labels I, J, K. For example, in the previous talk by Stefano, we saw a nice analysis of the HHLL, the heavy light 4-point correlator. And that's a very nice correlator to study. There's a lot of bootstrappy information you can extract from it. You can extract it in light cone and Reggie limits. You can also see from these types of computations to what extent a 2-point function of light fields in the background resembles or not, does not resemble a black hole background, etc. Now, one interpretation of the eigenvalue thermalization hypothesis is the statement that the OPE coefficient, so this OPE coefficient has 1 light and 2 heavy states in it, so it's a light, heavy OPE coefficient. If we ignore this diagonal term for the time being, then basically what the second term here is saying is that the light, heavy OPE coefficient is essentially a Gaussian random variable R, together with a certain amplitude, which depends smoothly on energies and so on. So you can interpret the eigenvalue thermalization hypothesis as a statement that this OPE coefficient behaves a bit like a random variable. And now the main upshot of this talk is that we're going to promote that this is not only going to be true for the OPE coefficients that have 2 heavy and 1 light operator in them. But we're going to propose something which we can call the OPE randomness hypothesis if you want, which is the statement that if you have a structure coefficient, an OPE coefficient, with either 3 heavy indices, with 2 heavy indices and 1 light index, or with 1 heavy and 2 light indices, that these all are essentially random variables with an approximate Gaussian distribution. By Gaussian distribution, I mean that they have 2-point functions. The width is not 1, it's not a Gaussian distribution with unit variance. The variance will depend in some way on the energies of the labels I, J, K, A, and B, and so on. So there will be a smooth function of the energies that multiplies it, but for the rest, it will essentially be treated like random variables. And the basic underlying intuition behind all of this is based on the fact that it's just very difficult for a low energy probe to distinguish high energy states from each other. So there's a few things that we know. There has been work in the past that has been suggestive of the statistical nature of these OPE coefficients. So rather than viewing them as a sort of collection of distinct numbers that obey some consistency constraints, the first paper that just get rid of this thing here, it's a bit annoying. The first paper, I guess, that looked at some more distributional properties of OPE coefficients was a paper by Papadopoulou, Ryskov, Espin, and Ratazzi from 8 years ago, where they looked at what kind of properties OPE coefficients would need to obey from a more statistical point of view if you wanted the operator product expansion and 4-point functions to actually be convergent. Because typically, if you compute a 4-point function, there's a sum over intermediate channels, and there's a sum over absolute squares of OPE coefficients times conformal blocks. That's the basic structure of a 4-point function. And if you want this to be a well-defined, this sum to be well-defined analytic function of the cross ratios, these OPE coefficients multiplying the conformal blocks need to have a certain growth, or rather they need to decay at a certain rate, at a certain exponential rate. Now in larger than 2 dimensions, the diagonal terms CIIA, so this is C heavy light, they can be extracted from the finite temperature 1-point function. And this was explicitly done in this paper. This should, I think, be 8. Oops. This should be 18, I think, not 16. So if you have a heavy light operator like this, you can imagine that if you compute the 1-point function of the light operator on the torus at high temperature, that 1-point function on the torus at high temperature is precisely governed by the CIIA OPE coefficient. Now, a 1-point function on the torus at high temperature, just based on conformal invariance, it can only have one particular form. It has to basically scale as 1 over the inverse temperature to the power, the conformal dimension of the light operator A. So up to an overall prefactor, we know how this thing has to scale. Well, we know how the 1-point function of the light operator has to scale with the inverse temperature. And then you can just basically do an inverse Laplace transform and you can figure out how these quantities CIIA have to scale as a function of the energies I.
Jan, I have a question. These arguments of yours, they're all for theories at finite temperature, or they also apply to at 0 temperature?
They are for now all at finite temperature because all the intuition and so on. There might be generalizations of some of this to 0 temperature. But I think we know less of that sector. So you could imagine, it's a very interesting question to go to 0 temperature and to go to take essentially a large charge limit, for example, and to redo some of these arguments. But I don't think we know generic answers in those large charge limits.
But the thing is, I mean, your argument that they go like the inverse temperature, that cannot be exactly right, because you know that in the extremal limit at 0 temperature, many of those 3-point functions are finite. And, you know, Stefano was just computing some of them. So many of those 3-point functions are very happy and frisky. So they should not go, maybe the 1/t is the behavior at large temperature, but you know, when you approach the 0 temperature limit, the 1/t should level into something constant, because you know they shouldn't vanish at 0 temperature. Again, we know by explicit construction, and I think you also computed some of them with Ilias and.
Yeah. So if none of what I say is relevant for 0 temperature, because what I'm saying here, this is a high temperature statement, and I'm using the high temperature scaling with the high temperature scaling of the 3-point function, the scaling with the temperature, to make this particular argument. It's a great question. What happens if you go to 0 temperature and, for example, investigate a large charge limit? There is some work on trying to use Goldstone boson type ideas to write effective actions in the large charge regime by people like, I think, Hellerman and Domenico Arlono, Susanna Reffert, and people like that. But I don't think there is a known universal statistical structure that can be uncovered there. That's a great question.
Okay, thanks.
So if you look at the off-diagonal OPE coefficients that involve 2 heavy and 1 light operator, and you look at the absolute square of that, they're kind of exponentially suppressed, and they were recently obtained in a very nice paper by Luca de la Cretas from a few months ago, basically from hydrodynamics, looking at the late time behavior of 2-point functions from a hydrodynamic point of view. And he was able to extract this behavior. There's a much more detailed expression, but this is roughly how everything scales from hydrodynamics. And then also, finally, last year, in a nice paper called Ye, Maloney, Maxfield, and Ciaris argued, by studying 2-dimensional conformal field theories, they argued basically that indeed the eigenvalue thermalization hypothesis can be extended to all cases where one has at least 1 heavy operator. And based on some detailed computations in 2-dimensional conformal field theories, they wrote down these asymptotic estimates for the absolute value squared of OPE coefficients that involve either 2 light and 1 heavy, 1 light and 2 heavy, or 3 heavy operators. And there's some detailed scaling behavior here that is valid in these respective regimes. So in 2-dimensional conformal field theories, we have some more detailed information. We also know the precise prefactor that should multiply this random Gaussian stuff that should appear in these 3-point functions. And this is the kind of smoothly varying prefactors that we would expect to appear. You obtain these expressions. So how do you obtain these asymptotic estimates for these OPE coefficients? Well, for that, you need to basically use all kinds of versions of duality. If you look at the first one, the light heavy one, that basically follows from crossing symmetry of the 4-point function. So what you do is you look at the 4-point function, and you look at the crossing symmetry of the 4-point function of 4 light operators. And then you know that if you go to the right regime, then in one channel, the exchange is dominated by heavy operators, but in the other channel, it's dominated by a light operator, by the identity. But you know that these 2 expressions have to agree. So from crossing symmetry, you can then, by equating these 2 expressions and making sure that the pole that you see in one channel is correctly reproduced by what you see in the other channel. That is, for example, how you obtain this expression here. And it's remarkable that you can get this exact answer without knowing the precise detailed structure of Virasoro conformal blocks. Because it turns out you don't need to know the precise detailed structure of Virasoro conformal blocks. You just need to know how conformal blocks in one channel map to conformal blocks in a different channel. And that answer is known explicitly in 2D conformal field theory. There's a similar manipulation by which you extract the second one by looking at the high temperature 1-point functions on the 2 torus. And then this heavy 3-point function. Where do you get that from? Well, that basically comes from a genus 2 surface, because you can, if you think about the genus 2 surface, you can imagine there is some limit. So if you roughly think of the genus 2 surface as 3 propagators that connect to vertices, which is like a cartoon version of a genus 2 Riemann surface, you can imagine that there is some regime where heavy states go in all the 3 propagators. And then you can use, again, this crossing idea and apply it twice to the genus 2 Riemann surface and map it into a much simpler expression. And that then gives this result for the asymptotic growth for the absolute value squared of the heavy OPE coefficient. So now I'm going to see what all this, so now we're going to take this proposal seriously and we're going to see what it implies. So we're going to, from now on, restrict to 2-dimensional conformal field theories, and we're looking at OPE coefficients for 3 heavy operators. So I'm now no longer looking at light, heavy, only at heavy. And we're going to look at this particular product of 2 of these OPE coefficients. And for simplicity, let's assume that the conformal dimensions of I, j, k, and Lmn are all roughly equal to each other. They're symbolically indicated here by capital delta. In principle, you could take them all different from each other, then it would just be a more complicated function of all the different conformal dimensions here. But just like in ETH, we would still be assuming that this quantity varies smoothly as you vary all the different conformal dimensions from each other. So then we can write a version of ETH. This is inspired by ETH, where the product of 2 of these random things is basically given by a symmetrized product of delta functions, because these things are completely symmetric in the 3 indices. So just based on the symmetry properties of this product, on the right-hand side, you expect to find these delta functions. We don't believe that the product of 2 OPE coefficients is exactly like Gaussian random variables, so there presumably will be some correction here. We're a bit agnostic about the details of this correction. But just like in ETH, well, actually, let me first say something about ETH. So if you go to ETH, the statement that these R's, the random matrices that appear in ETH are random matrices, is expressed by this first term on the right-hand side. So if you take the product of 2 of these random matrices, you just get a bunch of delta functions. And there's a delta AB because if A and B are not equal to each other, these are 2 independent random matrices and they will never talk to each other. Then if you also want an ETH-like structure to reproduce the correct 3-point functions of light operators, it better be true that the product of 2 of these random matrices on the right-hand side also contains a light OPE coefficient times the random matrix associated to a 3rd operator that appears in the OPE of light operator A with light operator B. Because if you have this structure, you can now see that if you multiply this also with a random matrix RC MN or something like that, and that RC that we would put here multiplies this RC and gives some delta functions. And then we get a non-zero answer that's proportional to CABC, which is precisely the OPE coefficient for 3 light operators. And surely the 3-point function of 3 light operators in a typical state should be proportional to that particular OPE coefficient, with some unknown function h that depends on the details of that 3-point function. So this particular statement about the product of 2 heavy OPE coefficients is in some sense some sort of generalization of this thing that's written here. The main difference here is that here the leading term was just related to the fact that we have 2-point functions. Here the leading term is not related to 2-point functions, but it's related to the genus 2 partition function. Because again, if you put all these indices equal to each other, then what this is computing for you, once you sum over all these indices with suitable functions of moduli and everything, what you get from that should be the genus 2 partition function in the regime where through each propagator you have a heavy field propagating. And then the analog of this 3-point function, so some higher order correlation function that's standing here, will show up as a correction to the product of these two random OPE coefficients. Presumably, one can uncover some of the features of this S by thinking about higher genus partition functions, just like some of these features could be uncovered by thinking about 3 and higher point functions in typical states and in the finite temperature system. But we have not done that computation, so we're not sure exactly what the detailed structure of this S should be. But we do assume, just like here, the expectation value here of this R is 0, that in this case, this is just some subleading piece whose expectation value we also assume to vanish. In other words, if we compute the expectation value of the left-hand side by averaging over some states ijk and ln, then to a good approximation, this term will just drop out. So in some sense, this is simply saying that this is just making it a bit more precise what we mean when we say that these OPE coefficients that involve 3 high energy labels are Gaussian random variables. So let's now apply this to the genus 2 partition function in a conformal field theory. So we take a genus 2 partition function in a conformal field theory, which I wrote kind of schematically. Obviously, the whole structure of the genus 2 moduli space is a bit more complicated than this, but we're interested in the regime where, again, you can think of the genus 2 surface as 2 vertices connected by 3 propagators. And through each of these propagators, we have some CFT degrees of freedom propagating. And you can imagine that to each of these little cylinders, there is some particular modular parameter QI that's associated to it. And if you have 3 different modular parameters associated to each of the 3 cylinders, then the genus 2 partition function will look something like the sum over I and j and k, c ijk, c star ijk, just times these different weighing factors. And as usual, we can express the QI in terms of the some parameter tau I that is reminiscent of the modular parameter of a torus. Now we're interested in the regime where I and j and k correspond to high energy or heavy states. So we take the limit where these 3 moduli, the tau i's, they all scale like I beta over 2 pi, where beta is the inverse temperature, and we take the limit where beta goes to 0. So this is if you want the high temperature limit of the genus 2 Riemann surface, where there is basically you have an effective high temperature through each of the 3 pieces of cylinder that connect these 2 vertices. And now we can compute the genus 2 partition function in this regime using this previous ansatz, this one here. And if we do all that, we get this particular expression here. And this you can evaluate by a saddle point approximation. And if you do that, you get this particular answer for the saddle point. So if you compute the genus 2 partition function in this particular high temperature regime, if you want, then this is the answer that you get for the saddle point. It's a bit reminiscent of a Cardi formula, except the coefficient is different. Now we haven't done anything yet because the whole place where this f delta came from to begin with was in fact the genus 2 partition function. So we haven't really computed something that we didn't already know. This is just an illustration of how you sort of use this ansatz in an actual concrete example. And what you're reproducing is simply the saddle point approximation to the high temperature genus 2 partition function. Now let's look for fun at the square of the genus 2 partition function. So I'm just taking the square of 2 of these genus 2 partition functions. So, and I took all the temperatures equal, and here we have the same expression again. Where delta again refers to basically delta here is really the average of delta I, delta j, delta k, and so on. And the same here. This notation is a bit schematic, but it's sufficient for my purposes here. So let's now look at the square of the genus 2 partition function. Obviously, this is just literally the square of the genus 2 partition function. So what you do is they're Gaussian random variables. So we can do this standard Wick contraction. And obviously what this gives us is just the product of this thing here times this thing here. And that is just equal to the square of the saddle point that we derived before. It is just the square of the genus 2 partition function. So I showed you that the square of the genus 2 partition function is the square of the genus 2 partition function, and that's a tautology. However, it gets more interesting if you realize, if you really properly treat these OPE coefficients as Gaussian random variables. Because if you properly treat these OPE coefficients as Gaussian random variables, there's also another way contraction you can do. Well, in fact, there's two more. I just wrote one. The other goes exactly the same. And the other way contraction that you could do is one where this Cijk is contracted with a C in the other genus 2 partition function, and the same for this one with this one. So if you do this, and you use this rule for the Gaussian nature of the Cijk, then whereas before we had a sum over 3 independent indices times a sum over 3 other independent indices, so there's in total a sum over 6 independent indices. Now there's only a sum over 3 independent indices. It's like a diagonal term. Because if you do the Wick contraction of this C with this C star here, there's only a contribution if the indices ijk are the same as the indices LMN. So this is a bit funny. It's somewhat reminiscent of structures one sees sometimes in other descriptions of chaos, where one has products of random faces times products of random faces. And almost all the terms cancel each other, but sometimes the diagonal remains and somehow seems to be a leading contribution to the answer. It's a bit an artifact of the way you organize the computation. Here also, this is in some sense a bit of a fake, because what we do here is we do the computation assuming that the C's are really proper random variables. They are not proper random variables, that's just an approximation, but if you make that approximation, then we get this extra Wick contraction. And now if you now plug in what the C's are and you use this explicit expression here for the product of the C's, and you use this answer for F, and you plug it all in for this non-standard Wick contraction, then we get the result for the non-standard contribution to the product of 2 genus 2 partition functions, which is written here. And now it turns out that this thing no longer has a saddle in the conformal dimension. The whole thing basically becomes R unity. So that's quite different from the previous one, which was exponentially large. So the total answer for this product of the 2 genus 2 partition functions in this Gaussian approximation is that we get the product of 2 genus 2 partition functions plus a weird extra order 1 contribution. So we see that this is just a number, so I can always take the square root of a number. But we can redo the same computation, including some moduli dependence, so some more detailed moduli dependence. And if one would include some more detailed moduli dependence, one would see that this is an answer which can no longer be written as the square of a single expression. So this Gaussian approximation to the OPE coefficients makes this answer non-factorizable. That's a mistake that you get if you assume that these OPE coefficients are purely Gaussian. Now, why I'm telling you all this, that is because this has an interesting counterpart in gravity, so this story. So I told you that we make a mistake if we assume that these OPE coefficients are Gaussian, and the mistake is an extra contribution, an extra apparent contribution in the product of in the product of 2 genus 2 partition functions, and the extra piece is something of order unity. So let's now do the gravitational computation. Now, we can redo all these computations using ADS3 gravity. This is all something we can do in pure ADS3 gravity. So we're interested in the case where the boundary is a genus 2 Riemann surface. the type of bulk solutions that we can write down, if the boundary is a genus 2 Riemann surface, simply correspond to choosing a bunch of cycles that we decide to be contractible. There's many different solutions depending on which cycles you decide to be contractible. You may remember that if the boundary is a torus, you can also choose an arbitrary one cycle to contract in the bulk. And this gives an SL2Z family worth of gravitational solutions. In this case, there's even more, because here we can take there's an even bigger choice of one cycles that we can contract. And that give rise to solid Riemann surfaces as a 3D geometry. And then you can compute, again, in the limit that you're interested in, what the contribution is from ADS3 CFT2 from the bulk to this genus 2 partition function. And the result that we get, if we do the bulk computation in the limit that we were interested in, right, which was the limit where you think of the genus 2 as 3 cylinders and where you imagine that the effective temperatures in all these cylinders is very large, so you have high energy states propagating. You can do this computation. I'll not give you any details, but the result was given in this paper by Maxfield, Ross, Way. And this is the result that you get for the genus 2 partition function. Now, if you think in gravity about the product of two genus 2 Riemann surfaces, then there's an obvious bulk solution, which is simply the product of two of these ADS3 geometries, of two of these handle body solutions. So in gravity, we definitely have this particular contribution to the problem, coming from two disconnected geometries. But now, interestingly enough, if the boundary, so this is a very specific feature of ADS3 CFT2, there is a very confusing other possibility, which is a wormhole solution, and the confusion was already pointed out in this paper by Juan and Liab Maus 16 years ago. So if you have a genus 2 Riemann surface, there is a very simple exact solution of the ADS3 field equations, which is a wormhole of this type. It's very simple. The solution takes this form. It's very simple if these two Riemann surfaces are identical and if we choose a metric on these Riemann surfaces so that the scalar curvature is constant. If the scalar curvature is constant, then this is an exact solution of the field equations. It's a bit reminiscent of the sitter. If you had put a minus in front here and replace this by a 2-sphere, it would look exactly like the sitter. But there is this funny duality between the sitter and anti-de sitter solutions where you flip the sign of the scalar curvature of the slice and you also flip the sign here. In any case, this is you can easily check that this is an exact solution. You can also compute the contribution of this to the gravitational partition function. And in the conventions that I was using, this simply gives 1. The reason is that to compute, this is actually very easy to compute. If you plug this into the action of ADS3 gravity, you just, this is a constant curvature metric. So all that you need to compute is the volume of this space. Well, that's very simple. If you compute the volume, because all that you get is some tau dependence, and then you need to integrate this tau from this side to this side. And then you get basically some exponential piece from this side and some exponential piece from that side. But both of these are killed by the counter terms that you need to include. And then there is a little finite ambiguity remaining, but you can simply choose that to be equal to 0. That's just a choice, that's some ambiguity that one has. And if you do that, then this thing is something for the unity. Now, this is a confusing object in gravity, because on the one hand, according to the standard rules of ADS-CFT, we think that this should contribute to the partition function of a genus 2 Riemann surface times the partition function of a genus 2 Riemann surface. On the other hand, it seems to be very wrong because this is not a factorized answer. So the precise status of this wormhole and its meaning in ADS-CFT has been confusing. Recently, Merrill and Maxfield also wrote a long paper where they went back to propose that all these wormholes are telling us that we need to average. At least that one interpretation of the existence of these confusing Euclidean wormhole solutions is perhaps that ADS-CFT is based on theories with averages rather than theories that are unitary and microscopic and so on. But I'll say something about that in a minute. In any case, there is this confusing wormhole solution. It is not obviously destabilized by anything. In higher dimensions, if you have negative curvature on the boundary, you have a field theory on a hyperbolic space, then you might think that because of the curvature coupling of scalars, that would typically destabilize those theories. But in 1+1 dimensions, there is absolutely no problem in defining a conformal field theory on higher genus Riemann surfaces. We can compute partition functions. So there's no obvious sickness or weirdness with this wormhole. It seems to be a completely reliable solution. And it gives this extra contribution Z is equals to 1. So the final result that we get, if you look at these gravitational saddle points, is this result here. And this ratio of the product of two genus 2 Riemann surfaces divided by the square of a single object, this combination here, it's 1, which just comes from the disconnected piece, plus an exponentially subleading term coming from the connected piece. That is exactly the same, including the dependence on C and beta as what we got from this Gaussian CFT computation, from the assumption that OPE coefficients are Gaussian. I think there's a question, Juan?
Yeah, so how did you argue that is exponentially subleading the connected solution? Is that a gravity result or a field theory result?
Both.
Ah.
So in gravity, we just did a computation both in the field theory using this Gaussian ansatz for OPE coefficients.
Yeah.
This exponentially subleading piece. Well, to be precise, so here I divided these things. But this answer is just an exponential piece plus something for the unity.
Mm-hmm. Mm-hmm.
And that's precisely the same structure that we also got in the CFT.
So you computed the gravity action of the lowest action solution with one boundary.
That's right, yeah.
Okay, fine. Thank you. So that one depends on the moduli though, right?
Yeah, so we took this in a very particular limit where a very specific corner of moduli space.
Oh, yeah, you took the 3 temperatures equal.
Yeah,
Oh,
yeah.
Okay, thank you. Yeah.
In principle, try to redo all these things with more complicated moduli dependence, but we just took the simplest corner of moduli.
Ah, okay, good, thank you.
Absolutely. Elias? It says Elias Carissa has raised hand.
Yes, and we can hear you. No, we cannot hear you. The microphone is on, Elias. Maybe the headphones are a problem.
He's muted again.
Yeah, okay.
I continue or?
Yeah.
Okay. Right. You could also consider other corners of moduli space, but as far as we can see, that will not have a major impact on the results. But it will be interesting to study the moduli dependence in more detail. So it looks from this point of view at one interesting interpretation of this genus 2 wormhole is therefore that it's a consequence of the fact that gravity perceives the high energy OPE coefficients as random. So if gravity will not have full access to the microscopic details of these heavy OPE coefficients. It will only see a coarse-grained version of these heavy OPE coefficients. And if it were the case that gravity only has access to these sort of statistical average values of these OPE coefficients, then there would be a perfect agreement between the gravitational computation and the field theory computation. And that yields that provides an interesting perspective on the to average or not to average question. Because one can say that if we do not average, so if we assume that the CFTs that we work with are microscopic unitary theories, there's no disorder average of any type, just a single theory, then what's the interpretation of this wormhole? The interpretation of this wormhole is that in this particular case, the wormhole is a mistake that gravity makes. And the mistake is caused by the fact that gravity has insufficient access to the high energy details of the theory. So what we should do in this case is we could argue we should throw away the wormhole because it's just a mistake that gravity makes. And when we say that it's a mistake, we use a little bit of information, namely that we know the actual answer. Namely, of course, the actual precise answer should just be the product of two genus two partition functions. So it's in this case, for this particular specific case, the wormhole appears to be a mistake that gravity makes due to its lack of knowledge of high energy details, which suggests that you should be careful when applying the semi-classical approximation in Euclidean quantum gravity and including saddles. I'm not saying it applies to all saddles, but for this particular case. It also seems to suggest that if we were able to introduce a suitable notion of averaging in the conformal field theory, so suppose we were able to make a disorder average in the conformal field theory, and suppose we were able to do it in such a way that these OPE coefficients did become properly random variables. I have no idea what kind of averaging that would be, but if you were able to do any disorder average in the CFT, and presumably it would require lots of parameters, in such a way that this ansatz for the OPE coefficients that we wrote down would become exact, they would become exact random Gaussian variables. And you can well imagine that in principle, something like this might be possible. Then the wormhole would not be a mistake, and then it should be taken into account. So in some sense, the wormhole is not telling us that, from this point of view, the wormhole is not telling us that we should do an averaging in the field theories. The wormhole, the lesson is that the wormhole is actually there and should be taken into account if you do average, but if it's a mistake, if you don't. So that is an interesting perspective on this to average or not to average question. I'm almost done. I guess I'm also close to the 1 hour mark. So there's many other interesting things to explore. This was just the beginning. There are many other regimes for this genus 2 example or higher genus example to consider. We could look at asymmetric moduli on the left and the right. We could look at correlation functions of light operators on various higher genus surfaces. We can look at try to even explore the non-Cardier regime. So what happens if you're not at very, very high energies, then there will be more details and there will be less universality. It would also be interesting to see if there are interesting quantum many-body type systems where maybe some of this can be numerically checked. Maybe there's a statistical version of the Bootstrap program that would be interesting to explore. What's also very interesting is that in the eigenvalue thermalization hypothesis, so higher order correlation functions imply relations between the random variables R, A, I, J. So they're not quite Gaussian. And there should be some similar constraints for the heavy OPE coefficients. So maybe something like crossing imposes further constraints on them or some other feature, but it's not exactly clear what that is. In some sense, for these random variables that appear in ETH, in some sense you could say that these random variables in some sense form a representation of the OPE algebra. Because if you take the product of two of those random variables, one contribution that you get is an OPE coefficient times yet another random variable. So it's some sort of random representation of the operator product expansion that apparently we are dealing with here. And it would be great to see if that's a mathematical structure that could be developed more. Related to all that is the question about this remainder term here. So this was the leading Gaussian ansatz. And just like in ETH, there had to be some extra piece there, which came from higher order correlation functions. We would also expect an extra piece in this expression. Oh, that's not good. In this expression, and it would be nice to explore the structure of this extra piece a little bit more. It's related to what I just said. What are actually the sort of extra pieces of data that we need to impose on these random OPE coefficients to get a more complete story. What I did was something in 2 dimensions, so it would be interesting to see what you can do in higher dimensions, where results for partition functions are much less universal. And it's much harder to find stable wormholes. As I already mentioned before, if you take negative curvature boundaries, you could in principle write down exactly the same solution that I wrote down in 3 dimensions, namely some cosine hyperbolic tau squared times a negative constant curvature surface. With those negative constant curvature surfaces, they would typically destabilize the theory. So wormholes in HS3 are alpha prime exact, so it's also interesting to go away from real strong coupling and to see whether there's even some notion of average OPE coefficients that say if you approach the symmetric orbital point. Again, taking all of this kind of seriously, if we think about the 1-point function on 2 tori, here is so if you take I equals to J and K equals to L, it's essentially describing a 1-point function on a torus at high temperature. This is also describing the 1-point function of some light operator at high temperature on a torus. Even in this case, we expect an extra piece to arise. So this would kind of suggest that maybe even in the case where you compute 1-point functions on tori, and you take this Gaussian ansatz seriously, there should be some sort of wormhole-like configuration contributing. Now, in gravity, I don't think there is a corresponding classical wormhole where one has 1-point functions of light operators on 2 tori. I don't think even in the presence of these scalar sources, they don't appear to be such classical wormholes. But it's certainly possible that maybe if you include back reaction, like some sort of Casimir energy that's created by the scalars, that might be able to support quantum, sort of a quantum wormhole. Or maybe there's a set of gravitational off-shell configurations that could explain this extra expression. So that would be an interesting prediction. If these things are really not there, then this is also teaching us something about the dictionary that we're developing here. So to wrap up, we are proposing here that semi-classical gravity corresponds to some combination of precise low energy and statistical random high energy data. There's obviously no sharp cutoff between the two. So as you increase in energy, somehow the precision goes down and it becomes more and more statistical. Everything I said is a natural continuation of previous observations, such as the eigenvalue thermalization hypothesis. Also the fact that spectra of chaotic systems are well approximated by random matrix theory and all that. And it would be very interesting to make this framework more precise. I already said a few things about it. What's the right language to use? Should we try to look at random algebras of some sort or another? It seems to be a bit of an elaborate structure that one needs. I don't know what kind of thing that should be. There have been attempts in the past to relate certain random properties to things like non-commutative probability theory and so on, for example, in matrix models and all that. And this goes back to ideas that, for example, in QCD, there should be a master field that controls all the correlation functions. But that seems to be too simple. That's just sort of just ordinary random matrix theory to some extent. We clearly need something where we don't just look at random matrices, but also at a notion of random products of matrices, so random algebras or something like that. So I don't know if there is a mathematical framework to capture these kinds of things, but that would be certainly interesting to explore. That's it. Thank you.
Thank you very much, Jan. Very nice. Any questions, guys?
Let me first allow everybody to unmute themselves.
Oh, yeah.
And Jan is now muted, so I just unmuted him. So anybody who has a question, they can unmute themselves. I think Elias had a question, and I think his microphone didn't work. Maybe now we are in a better.
Questions, comments?
Hi, this is Samir. Can I ask a question? Actually, it's more like a comment. It's about the starting part of your talk where you were mentioning what gravity might or might not be able to see. I just wanted to observe that when you try to make this dictionary between CFT states and gravity states, one of the early things which were very interesting to me was what we learned from the PP wave story that Juan and the BMN developed. So there was a nice paper of Gaba and Narayan which showed us that the fractional modes on the multi-wound strings, they are the ones that correspond to strings in the PP wave approximation. So we already know that somehow if you want to look at the microstates on the gravity side, it's not really the smooth ones, which are the easiest ones to start with, of course, but you actually find strings in them and so on, and we know what they correspond to on the CFT side. But what's also interesting is that if you take a condensate of such strings, like you take many of them, like let's say you take all the CFT copies and you put strings on all of them, it again actually makes a condensate which can be described by classical supergravity. That's something we showed in a paper more recently in a very simple case. So somehow the gap between what you can see in terms of smooth supergravity things and what things are stringy, there's no real sharp gap there, because you can on the one hand see stringy states in your microstates, and then on the other hand, you make a condensate, you start seeing classical things again. So it's not a sharp question for you. I'm just saying that what you can actually see in gravity, I think, really should be complete, because there's a one-to-one map in ADF-CFT between what you see in the CFT and what you see in gravity. And I think there's no sharp point where you can say, well, gravity shouldn't be seeing this. Gravity is only an approximation that throws away this. I think ultimately gravity should see everything. I just like your reaction on that.
So yeah, sometimes these discussions end up being somewhat semantic, but I think gravity is probing. It's not string theory should see everything. But if we talk just about the graviton or something like that, it's just one particular field. And if we mean by gravity should see everything, that by integrating out all other degrees of freedom and only being left with the metric, we should still have access to all the information. I think that's just from an effective field theory point of view, that seems very wrong. So it depends a bit on what we mean exactly by the sentence that gravity sees everything. If we mean,
I actually did mean string theory. I did mean all of string theory, and I was saying I don't want to integrate out the stringy parts, because then what you're left with will probably be very non-local.
Right, but if we keep all the stringy parts, then I would imagine that, although I don't know how to solve strongly coupled non-perturbative string theory, then obviously we have a different, possibly complete starting point. But this we don't, as low energy observers, I always think of gravity as somehow a synonym for low energy observers and low energy effective field theory. And I think low energy observers certainly do not have access to all of that. If we allow stringy probes, if we allow, if we can have arbitrary high energy experiments and everything like that, then I would imagine we should be able to see everything. And unfortunately, we don't have access to those things. So.
Okay, thank you. I understand. Thanks.
Any other questions or comments?
Elias, maybe now we can hear you. Elias is having problem with the headphones, and somehow I cannot hear him at least.
While he's sorting out.
Wait. Sounds like we can hear you. You can always write a question if you can't. So in the meantime,
maybe following up on
yeah.
Samir's question. So this two-sided wormhole solution is completely fine in the pure 3D gravity theory. But if we embed it in 10 dimensions, then it seems that you can nucleate brains that might either go to infinity or maybe might be localized on some finite side. I'm not sure whether it could be made completely stable. This is
Now, thing to figure out. It's possible that there's a mechanism that destabilizes it or that moves it into a different solution. But I think this has not been spelled out in the.
But on the other hand, I don't see exactly what the principle is that removes this type of contributions from appearing. So, and I think it's not the issue is not perturbative, but more non-perturbative. So not so much like the stringy degrees of freedom, but I don't know, exactly how we think about the full string field theory path integral, whether we do or do not allow these connected contributions. And it could well be that the problem is still there in string theory, except that maybe we don't have a really super crystal clear example.
So may I ask a question?
Lots of other,
That's the answer. Go ahead, Jan.
So in string theory, there would be lots of other things that would be difficult to compute in full string theory. And it's conceivable that if you included all kinds of stringy corrections to this, that you would reinstate a factorized answer. I mean, this kind of structure that you see if you take a sum of random phases times the complex conjugate of that sum, that there is some resonant diagonal term. So this could be very much like that resonant diagonal term. That's kind of useful. But then the stringy degrees of freedom would be all these off-diagonal complicated detail things. But if you would resum the whole thing, you would get a perfectly factorized answer. That's more how I was thinking about these. So it's perfectly fine that it's there maybe as a contribution in gravity. But you can see from this random OPE approximation that it's kind of capturing some sort of diagonal of some complicated object, if you want. That's more the perspective here.
Emel's got a question. Go ahead, Emel.
Yeah, so there are other situations in which one gets connected wormholes by taking multiple copies of a CFT and by hand introducing some sort of additions to the Hamiltonian, which are products of operators in the separate CFTs. So this is, for instance, the way that people made traversable wormholes. Could you comment on the relation of that to the sort of statistical averaging you're doing to get connected geometries?
Yeah, that's an interesting question. I don't know the answer. I don't know if you can see that. Yeah, this kind of torus thing. So this statement about the products of one-point functions on tori, it could be that so if there is a quantum wormhole here, if you include some back reaction, then maybe that's in spirit. If that, I don't know if it exists, but that could be in spirit kind of similar to what happens if you introduce these non-local correlations between two disconnected boundaries. So for example, in this Gauss-Jeffreys and Wall version of the wormhole, they included this left-right coupling in the theory. It's not exactly the same as this, but there also some quantum back reaction was needed to open up the wormhole. So maybe that's in spirit, not maybe a bit like these types of expressions written here.
I mean, it is the sort of thing that sort of by hand destroys the sort of factorization that you started with.
That destroys it by hand. Yeah. So in this case, this is for an uncorrelated one-point function. So this does not introduce correlations between the left and the right. So in that sense, this is different. If you by hand introduce correlations between the left and the right, which you could do in many ways, then obviously there would be properly, there's no reason why you cannot have wormholes that are completely reasonable from that point of view. Yeah, I agree. So this is not the same. So I don't. If you add these correlations by hand between disconnected spaces, whether that has whether one needs this random machinery to give a nice interpretation to those wormholes or not is not clear to me. That could be have a much more mundane explanation.
Jan, following up, if I stay agnostic to whether I introduce these correlations or not, do you have anything to say about Lorentzian wormholes? You've you talked about Euclidean wormholes. If there are Lorentzian wormholes, whether I produce them through some correlation or not, if I just see them as saddles. Do you have anything to add?
No, I don't have any interesting. I think the Lorentzian story is somewhat different, so I don't have an immediate interesting new insight to offer about the Lorentzian case. If you could organize suitable Lorentzian cases, like if there's a particular interesting Lorentzian computation, which is again interpretable in terms of statistics of OPE coefficients, then one could see, but this probably would require a somewhat complicated setup, just like genus 2 times genus 2 was needed here. But if you could engineer a Lorentzian version of that computation where these OPE coefficients of heavy would appear naturally, then you could imagine that this would predict a wormhole in those cases. Yeah.
But where would you start if you started?
Sorry?
What would you do if you had a bulk solution, for example? What you're saying is how to look at it from the CFT.
You want to see how you dynamically create these things?
No. I'm just saying if there was a Lorentzian wormhole solution in the bulk, the OP is in the boundary theory.
Well, if you give me some Lorentzian wormhole, it depends a bit. You would try to translate whatever happens in the bulk, I guess, in some sort of CFT statement. So maybe there would be two disconnected boundaries. Then you would try to see what kind of computation this thing is supposed to. Well, you would ask what is the CFT computation that this thing is contributing to? Is that some correlation function in the CFT, or what is the CFT computation that this weird configuration is contributing to? And once you translate it into a CFT computation, you can try to re-express it using OPEs in terms of these objects. And then you could see if you see an image of this wormhole in the CFT computation. That is, I think, all you can do right now.
Thank you.
Any other questions, comments, concerns?
I think Elias had a question. Is the Maldacena-Mao solution a smooth solution, or it has orbifold singularities at the boundary?
No, that's a smooth solution.
Elias, I don't know, your microphone is still on or not. And there's another question by Stam Nicolis, but I don't know.
Yes. Can you hear me?
Yeah, go ahead.
Yes. Okay, let me do. I'd like to ask the following question, because when you impose the conditions of the eigenstates normalization hypothesis, there is, on the one hand, there is this Gaussian random variable that appears. But on the other hand, there is an explicit temperature that appears, right? There's a factor. There's a beta that does not seem to know anything a priori about the properties of the Gaussian distribution. And so I'm just asking, how are the two, if they are, how are the two related? Because then you said that you want to make an average, when you say whether you average before or after, the average is with respect to the Gaussian distribution or with respect to the thermal average that is defined by the temperature that you put in additional. And that's related to this Euclidean wormhole business, because of course, when you're doing a Euclidean wormhole, that should know something about the temperature. Is that correct?
Yeah. So the temperature comes in enters through the weighing, like the temperature, or if you want the moduli, because in the genus 2 case, rather than temperatures, you have moduli, but it is sort of the same thing. What you have is that the full partition function is the sum of absolute values of c squared times a function of the moduli. And that function does not just depend on the moduli, it also depends on delta I, delta j, and delta k, but in a smooth way. And then you can evaluate using a saddle point approximation or something, these types of sums. So the temperature, there is a difference between the temperature dependence. So suppose you compute a finite temperature partition function, then there is just an explicit temperature which appears in your Boltzmann factor, right? But then in ETH, there's also like an entropy appearing and all that, but those are not related to whatever your canonical temperature is. They're just related to the energies of the eigenstates. So you have in mind in some sense, you're already using thermodynamics because you can always relate an energy to an entropy and to a temperature in some system. And they sort of, when you write S, you mean the entropy at the average energy of the two eigenstates. And if you write a temperature in ETH on the right-hand side, you mean the temperature that corresponds to that average energy.
So the averaging would be with respect to the properties of the Gaussian distribution that a priori don't know anything about the temperature.
No. That's just the Gaussian distribution knows nothing. That's just Gaussian. It's the prefactor. It's the variance of the Gaussian distribution which knows about the energies of the state.
Any other questions? Okay, well, let's thank Jan again, and we will resume at in about 15 minutes for the panel. Or let's start things setting up 10 minutes from now. Thanks, Jan.
I'll start meeting. I'll meet everybody again.
Okay.
Okay.
Okay, I just unmuted you, Suvrat.
Yes.
So how do we, Jan will disable who goes first, or how does it go? Or you're moderating. Oh, sorry, you're the one.
My plan was to follow what was given on the schedule, which is alphabetical by first name, it seems.
It was kind of random, but if the panel has a different order of desire, then that's also fine. But
No, that's fine. Yeah.
So before I hand it over to you in a few minutes, David, I'll just make the usual statement about rules of engagement and all that.
Sure.
And then
I think also when Joseph gets back, he should. Oh no, somebody's already made Suvrat a co-host. That's good.
I made Suvrat a co-host. Yes.
Yeah.
Great, thanks.
The pixies are at work.
Should I mute everybody and leave?
No, I think let's just see what happens. I think let's just keep it as free for all. We haven't been Zoom bombed, so let's just go from there.
Okay. Yeah, Juan is asking me if I can use. Juan wants to use his iPad.
Yeah, I think we resolved that, Joseph. It seems.
No, but I need to make the Juan's iPad co-host in order to be able to share.
Oh, indeed.
Oh, it's a separate.
Well, we managed to share it successfully.
Yes. No, but it's not that. I mean, the question is, whether in case there's a problem, we may not allow to share. So.
Okay.
So, everyone can share screens, right? So I'll join also with my iPad if I need to write something.
You're a co-host. You can. Oh, if you join from an iPad, I need to make your iPad co-host as well.
Oh, okay. Let me join from an iPad as well, and then fine. Thanks.
Okay. Yeah. The only concern that can happen is if you've got two things in the same office and the audio.
No, I'm going to mute. I'll mute the iPad so that it shouldn't be feedback.
Okay.
You have to mute and cancel the microphone of one of the devices.
Right. Yeah. No, I'll do that. Yeah, with the iPad.
Did you join?
No, just a second. I have to find the Zoom ID again. Please, 996.
No, you don't need to. No. Oh, the Zoom of the meeting. Yes. Sorry.
Yeah. 86502. Okay.
So how is it called?
Yeah, it's Suvrat Raju iPad.
Oh, okay. I just. Yep. Okay. It's co-host as well. So.
Okay, great.
Okay, it's 5:45, so perhaps we should start the ball rolling. Basically, the rules of engagement are that David Turton is the moderator and traffic cop and everything else. And basically, the plan is to have everybody speak for about 5 minutes each and then throw it open to the audience for questions and comments. So over to you, David.
Okay, thanks. And so like the previous days, let's hold the comments and questions from the audience until each of the panel has made their introductory remarks. And we'll be following the order given on the schedule. So that's alphabetical by first name. So we'll have Joseph, Jan, Juan, Samir, and then Suvrat. Okay, so without further ado, over to Joseph.
Thanks. It was fun yesterday. My first name was the last on the list, and today is the first on the list. So somehow the first names are very different in the 2 days. This is just a very quick. It's a very quick review of some work on ADS2, which I did with David, and also some discussions with Miguel Paulos. Essentially, it's about ADS2 solutions. So we know very well that one can construct a huge amount of geometries, which have an ADS2 ultraviolet and an infrared cap. So the geometries here, they are all ADS2. So you get the usual ADS2 throat, but instead of getting an infinite ADS2 throat, you have a cap in the infrared. And the cap is basically breaking conformal invariance. And these solutions are dual to ground states, supersymmetric ground states of the CFT 0 plus 1, dual to this ADS2. This is just basic ADS CFT correspondence from 20 years ago and more. Now, there's another question which you can ask. Great, this CFT 0 plus 1 has conformal invariant BPS ground states by construction. You can also ask, does the CFT also have a conformal invariant BPS ground state? Does it have a ground state where conformal invariance is preserved? And this ground state would correspond to a solution which again has an infinite throat. It's on the left. I cannot show the mouse for some reason, but I'll go without. So it has so this solution has a conformal invariant. So that solution would be just dual to an uncapped ADS2. So just an ADS2 which has a UV boundary and then goes on forever. That's the solution if you take which obtain if you take the near decoupling limit of any extremal black hole in any theory. So the question is this solution dual to any ground state of the dual CFT to a conformal invariant ground state? And the answer is no. Why is that? In order to see that, there are some arguments which you can make, which are quite straightforward. That in a CFT1, if the CFT1 has a conformal invariant ground state, then you can see easily from the 3-point functions that all correlators of that CFT1 have to be topological, meaning they don't depend on t minus t prime, they only depend on the ordering of the operators. And moreover, you can argue that the Hamiltonian is 0 as an operator and the dimension of all the operators are 0. Now, if you look in the usual ADS2 times whatever you obtain in string theory, so you compactify string theory on, you get ADS2 times S2 times T6 or whatever ADS2 solution you obtain in string theory, because you compactify string or M theory on some 8-dimensional or on some 7-dimensional or on some 9-dimensional manifold, you get a huge amount of KK modes, and these KK modes have many dimensions. So whatever ADS2 solution you obtain in string theory, it will have operators which have many dimensions, and therefore by this argument, by the argument above, these CFTs are not going to be topological, and therefore they will not have a conformal invariant ground state. Moreover, for many of the CFTs, you can actually construct supersymmetric solutions which are capped, and again, they are dual to BPS ground states which break conformal invariance. So we know that these CFTs, again, by this argument, they do not have a conformal invariant ground state. And on the other hand, you can actually build for many of them holographically. You can argue that they have ground states which break conformal invariance. And therefore, the point of this argument is that empty Poincare ADS2, the one which again comes from the naive decoupling limit from the decoupling limit of the extremal black hole, that empty Poincare ADS2 is not dual to any ground state of this CFT 0 plus 1. In a sense, it's similar to Poincare ADS3. Poincare ADS3 also is not dual to any ground state of the D1E5 system. The ground state of the D1E5 system are given by supertubes, by Lunin-Matur and Lunin-Maldacena-Maus solutions. Those are the ground states of the D1E5 of the dual CFT. The empty Poincare ADS3 is not dual to any of this vacuum. Moreover, you can build an infinite tower, a finite energy excitations about all these geometries. You can take many of these asymptotically ADS2 geometries to the cap in the infrared, and you can actually build excitations on top of them. And when you glue these solutions, these ADS2 solutions back to ADS3 or back to flat space, you see that these solutions can be glued with a longer or a shorter throat. And then there's a very clean calculation which shows you that, for example, the ADS3 mass gap, which you get out of these excitations, is going to be the smallest in the CFT2 when you have the longest possible throat. So essentially, the finite energy excitations of this 0 plus 1 dimensional CFT are just dual to excitation. They have exactly the same wave equation. They have exactly the same form as the excitations of the 1 plus 1 dimensional D1E5 CFT above, which break supersymmetry. So again, you have this. You have all these solutions, and they glue very easily, and their physics matches very easily to the physics of the D1E5 system. Now, the question is, first of all, people are saying, oh, in ADS2, you cannot build conformal, you cannot build excitations. There's a problem with excitations. Indeed, if you look at an infinite ADS2, you cannot build excitations there. But as I argued, from a holographic perspective, the infinite ADS2 solution is not dual to a state of a single CFT. There's a CFT living on so the Poincare patch, the Poincare ADS2 is not dual to a state of the 0 plus 1 dimensional CFT dual to that. And to make the ADS2 into a good solution, you have to put an infrared cap. And then, of course, once you do that, you can build, you can put excitations as many as you want, and life is nice and beautiful. But again, you have to realize that, again, empty ADS2 is not dual to anybody. The second question is, what about ADS2 toy models where the infrared cap cannot be present? There are many toy models which people build for ADS2. One can just build, you know, Jackie Teitelbaum, but you know, there are many other simple examples. What I would like to claim is that the simple examples where the ADS2 cannot be capped do not capture some of the physics. And again, WAF, I would say that they're in the swampland. Again, this slide, the last slide is quite provocative. And the point is this argument that, again, asymptotically, that essentially the solution which is just empty Poincare ADS2 is not dual to any of the dual CFT states, essentially would be the quickest way to prove the fast proposal. Essentially, what we are saying, what this argument shows, is that the black hole solution is not dual to any pure state of the 0 + 1 dimensional CFT. It's not dual because, again, all the ground states of the 0 + 1 dimensional CFT break conformal invariance, while the black hole solution doesn't do it. Now, one thing about the microstates which you obtain, again, all the ground states break conformal invariance, but this doesn't mean that they're going to be smooth in supergravity. The only thing we know is that because they break conformal invariance, they do not have a horizon, but this doesn't mean that they are smooth in supergravity. Moreover, this argument establishes that the fast proposal is correct only in asymptotical ADS2 solutions. Now, there's a problem. First of all, many of the asymptotical ADS2 solutions which you build, many of asymptotical ADS2 cap geometries which you build, sometimes they do not fit into ADS3, and moreover, they do not extend to non-extremal black holes. So one could say, great, you know, this works for asymptotical ADS2 solutions. You proved this version of the fast proposal, but this doesn't say anything for ADS3 or for flat space solutions. And moreover, because non-extremal black holes don't have this ADS2 region, this argument doesn't extend at all to non-extremal black holes. So those would be the counter arguments. Thanks.
Okay, thank you, Joseph, and thank you for keeping to time. So we'll pass on directly to Jan.
1 second here, let me see. I need to share my screen. So, yeah, I will just make a few remarks. Also to try to, I asked the other people, I had the advantage that I asked the other people what they were going to say. So I tried to say something which is not the same. So the question, I think it's very good to try to make the question more precise, because the question, do typical states have horizons, is maybe not as precise as one would like it to be. So let's try to see if we can elaborate a little bit on a few aspects of the question. So first of all, if we want to relate a state to a horizon, we are relating a state, a quantum state, to a geometry, which means we're doing a map from quantum physics to classical physics. And I think the operational way we could think of doing this map is to compute one-point functions of simple operators in this particular given state. And then we use this as boundary conditions for the classical bulk field equations in ADS. That, I think, is operationally how we map quantum states to classical geometries. At least that's how I would probably do it in ADS. If I were forced to associate a classical geometry to a quantum state, and I would probably do this. Now, associating classical things to quantum things can be murky, especially at finite n, but obviously it becomes better and better as n becomes large, but you're always sacrificing a little bit. And a similar problem arises in quantum mechanics if you look at discussions of phase-space densities, which is also a version of mapping a quantum to a classical problem. So if you follow this procedure, then any state, it could lead to a singular geometry, you could get a smooth geometry, and you could get a black hole. But do these geometries actually mean something, or are they garbage? Well, for that you have to see whether the geometry is in some sense classical, and one way to diagnose that is to look at, for example, variances of one-point functions. Because if these are large, then we have a quantum state where classical observables have large quantum fluctuations. Those geometries we would probably say are rubbish. So in that case, these geometries probably should be not viewed as actual proper geometries. And to preemptively answer a question Samir might be asking, so if we could compute the one-point function of all stringy operators, and solve the full string field theory equations of motion, then who knows what will happen. But I don't think that's a realistic program to execute given current technology. This annoying thing, yeah. Now consider a typical high energy state. And suppose that it has a good geometric description in the above sense. We compute one-point functions, we solve the field equations, and we check that variances are small. So it's a coherent state or some other nice state with a nice approximate classical description. Now, since it's a typical high energy state, then again, according to thermodynamics, chaos, blah, 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 you might expect that simple correlation functions in this high energy state would be the same as thermal correlators up to great accuracy, maybe exponentially suppressed accuracy. If that's true, then you would think that the geometric description that you would associate according to this operational procedure to a typical state would be that of a black hole with a horizon. Now, there could be a basis of atypical states that each separately look reliably geometrical. Like a typical fuzzball solution, for example, is not really thermal in the sense that there are obvious 2-point functions and 1-point functions that are different from what you would get in the thermal ensemble. So those we could probably think of being atypical states, but it could be that in some microcanonical window, there is a basis of atypical states that each look reliably geometrical. That would be great because then you would at least have access to a full basis of states. But this would lead to the situation where the quantum superposition of well-defined classical configurations leads to another well-defined classical configuration. Now, I don't know, maybe someone knows. So I would just like to ask this question. Does anyone know a situation in quantum mechanics where a superposition of well-defined classical configurations, a quantum superposition of well-defined classical stuff leads to another well-defined classical configuration? I think the feeling that this is very difficult is one of the reasons why some people might instinctively object against this scenario.
Unless you throw away the black hole. You just said the black hole is not dual to anybody, in which case, you know, you only have the classical configurations.
Well, I'm trying to make I'm not sure whether you say something else than I'm saying, but so if the black hole is not geometrically reliable, maybe it's not, but I would think that all these fluctuation computations would give very small answers. You might also imagine that if it's really a quantum superposition of reliable other classical configurations, that it would decohere into one of these other classical configurations after suitable measurement by, say, an observer. But it's a total mystery to me at last, but maybe someone has some idea of how to set it up, what a dual CFT computation would be that would show this behavior. There has been work on tunneling into microstates, but that samples everything with some probabilistic distribution. You don't tunnel into a particular state from that point of view. So how you would set up a measurement that would decohere a black hole into one of these atypical basis states in a CFT computation is mysterious to me. Then the final few comments are, so if the geometry, if this reliable geometry has a classical horizon, so then we could say, then this state has a horizon. But then it's still, the question is what we actually mean. So then a more refined question is that, you know, what will the infalling observer observe? And again, I think we still lack a very sharp CFT version of the question. Like, is there a particular, because we're talking about the experience of an infalling observer. And I don't think anyone has ever translated that into a razor sharp CFT question.
Jan, I wanted to make a comment about your previous slide. I was having trouble unmuting my computer. Would you be happy with an example from SYK for superpositions of geometries being a different geometry?
I would be happy to see and look at any actual example.
So there's an example in this paper of Colo and Maldacena, these microstates for in black hole microstates in the SYK model, where you can take a set of microstates with some length with sort of with a black hole of some interior length, take a superposition of them, a quantum superposition, and get a black hole with much longer throat. So you can actually do that if you believe in the duality between these black holes in JT gravity and the SYK model. But so
and all these states are, and all these states have small fluctuations.
I believe so, yes.
Sorry, but okay. So sorry, I'm not to interrupt you too much, but I don't think this basis idea can be taken too far, even if you found an example of this kind. And I think the reason is there are also statistical limits on the atypicality of a basis. And the reason for that is you can actually compute the fluctuations of the metric using the Euclidean theory, just by computing 2-point functions of the metric. And the fact that those fluctuations, which are suppressed by Hawking radiation, are down by 1 by s, also tells you that most basis elements cannot be atypical. So, even if you could find in one example some set of basis elements which added up to another classical geometry, most basis elements can't be too far away from the mean.
One second. I just want to allow everybody to unmute themselves. I just made, because Ahmed couldn't unmute himself. Now I think everybody can unmute themselves, and Jan, I just unmuted you, and Ahmed also.
Okay,
let's go.
I think Nick is about to do what I'm exactly about to do, which is just to propose that we let Jan finish his introductory comments.
I was almost done, thanks.
Thanks.
Let me see. I'm unmuted, yeah. So is there what's the razor sharp CFT version of this infalling observer question? So just to throw a slightly different version of the question, into the game, I wonder, so this is just an open question, whether, so we have been looking at these heavy light correlators, whether the detailed analytic behavior of these kinds of correlators is able to shed some light on what's going on behind the horizon to the infalling observer. And I'm saying that because if you're in the thermal field bubble state, you can reconstruct to some extent a la HHLL what goes on behind the horizon. If you take these correlators and you sort of analytically continue one of the time variables to the other side by shifting it to plus I beta over 2 or something like that. So if you have full control over this correlation function analytically, you might be able to do some HHLL reconstruction of stuff behind the horizon. But maybe if you have an actual microstate, rather like a typical state rather than a thermal state, maybe this analytic continuation breaks down, maybe in e to the minus s distance before you would reach the left boundary. And maybe those very small, tiny little features of the state psi are important to bound to what extent infalling observers still see no drama or something like that. So maybe one way is to look at these correlation functions to go to very late time, because if you just wait long enough, effective field theory breaks down and you can resolve E minus S energy differences. That's kind of a boring version of the question. Maybe the analytic continuation version question is a bit more interesting. And maybe the infalling observer sees nothing as long as correlation functions of this type have a suitable range where they can be analytically continued without hitting singularities or poles or something like that. Those were just some loose thoughts. I'll stop here.
Okay, thank you very much. So next we have Juan. And although all the interruptions were very interesting, let's try and minimize them until the rest of the panel has done their introductory remarks. Juan, we don't yet hear you. Maybe you need to unmute whichever device you're going to use the audio from.
Okay, can you see it now?
Yes, we see it and we hear you. Thanks.
Okay, wonderful. Thank you. Sorry for the delay. So I guess I'll simply I'll simply say how I think about this question. I mean, it's a bit of speculation, but so the idea is based on tensor networks. I think they give us an interesting perspective on how we could build space-time. So tensor network was invented as a procedure for building a complicated state in terms of simple parts. And there are all kinds of tensor networks. Now, Swingle pointed out that these tensor networks have a structure. So if you have a one-dimensional theory where you have, let's say, one space dimension, then we can have an emergent dimension which comes out of the structure of the network itself. And that has some similarities to the extra dimension we have in gravity. So then one can understand this, one can use this tensor network idea to understand why the black hole interior grows somehow. So when you evolve from, let's say you start with the thermal field double at t equal to 0, and then you go to some later time in the future, moving both times to the future, then you find that basically the spatial slice grows, and you can qualitatively understand that as saying, well, you have first some state which has this relatively simple entanglement between the two sides, and then as it grows, the entanglement grows, and not only the entanglement grows, but the complexity, the quantum complexity of the state grows. So the idea is that the structure of the tensor network is constrained by ideas of complexity, in the sense that it is the simplest way to prepare the state out of simple gates. And so if we have a pure state black hole, which is what we're discussing now, we imagine that we picture it as a very long tensor network. So first, so we could imagine that we started with some very simple state here in the past, let's say product state, and then we apply a bunch of gates. The gates need not be all equal, they're different, and then eventually we get to the structure of the UV here at the boundary. And so that suggests that such a state would have a very long interior. So, I mean, we don't know the precise correspondence for the typical state, but the idea is that it would be a very long, a state with a very long interior. This is what this picture sort of tells you. Of course, it's a conjecture, it's not a derivation. Now, the question that I guess Jan raised is whether there is a basis of states that is very simple. So you might imagine that there is a basis of state that is very simple at t equal to 0, and that basically looks like the ordinary black hole geometry and then some kind of end of the world, but maybe it's provided by some very complex topology and so on that we have near that point. And there are some states that are vaguely like that, which are the ones we discuss in the SYK model. And so this would be a very special pure state. You might have a bunch of topology, perhaps without interior. So this is maybe how I would perhaps picture this instantaneous fastball. So it's a fastball or a state that exists at t equal to 0. But from this picture, I would expect that it, as you evolve in time, it would evolve into a geometry that develops a horizon. So something like this. So at t equal to 0, we have maybe an end of the world brain here. But as we progress in time, this goes behind the horizon. So playing on what Samir was saying, so these simple states would be like what he was calling Velcro states. But then you can add this Velcro hypothesis, which is that when you sum over such states, you get a smooth geometry. So maybe those states exist, that bases exist, but the structure of the tensor network implies that in some cases we sum, so we could consider that state, that's a legal state, but in many other cases we end up summing over states of that kind, and that is precisely this sum that produces a smooth geometry behind the horizon. So in the thermal field, well, the thermal field double is a well-known example where we imagine that we would be summing over this, and then if we have a one-sided black hole, we are summing over these states with some complicated coefficients, and you can view the bottom part of this network as providing construction of those coefficients, and then along the dotted line, we are just summing against these apparently special states in order to build the full smooth geometry. Okay, that's all I wanted to say.
Okay, thank you very much. So next we have Samir. Samuel, you may need to unmute yourself.
Am I on
Okay.
screen share?
Yes, we see your screen. Thank you.
Okay, let me try to go to full screen.
Okay.
So I just have 3 slides on which I have put in here an outline of how I think about the puzzle. And on this first slide, I just list the information puzzle. And these are the various bits of the puzzle which I have phrased as points A, B, C, D, but they're actually more like questions to people like Juan or Subrata, Jan, who may disagree with the picture. I would just like them to think about, well, which of these statements they would like to modify or disagree with. So let me just make them as statements and then people can disagree with them. So in the traditional picture of the black hole, I would argue that it does make sense to draw like a ball-shaped region here, like I would draw in the middle of this room, and then I could ask, what is the state there? And then the traditional black hole, I would say that state is basically like what we think of as the vacuum in this room, up to small corrections. Second point is once you have a state like that, it will automatically produce entangled pairs because we can't stop that from happening. And then we know that if you make small corrections to that evolution, if the actual evolution wasn't rare, that the blue dotted line means some effect of quantum gravity from maybe submitting saddle point something in the Lorentzian section amounts to these small corrections. Then we know that that itself can't solve the puzzle, except as Subrata and other people have also pointed out, this proof really assumes that degrees of freedom far from the whole are independent of the bits in the whole. So with that assumption, we know we can't get out of, if we have that assumption, we can't get out of that puzzle easily. And I also want to note that there is no way to hide information in the vacuum. I mean, sometimes people say that, at long wavelengths, like a meter or longer, it looks like semi-classical physics, but what's happening at the Planck scale, that could be slightly different in the black hole geometry, and that's where the data is. But at least with normal understanding of field theory, you can't do that. I mean, if in a ball of radius 1 meter, the ball I took here, the lowest state is called the vacuum. The next state is, 8 dagger, 1 particle in the vacuum, 2 particle in the vacuum. And if you want to change the physics of the Planck scale, you add an A dagger k with k of the order of Planck scale, you will actually get Planck density of energy, and the whole thing will be Planck curvature. So you really can't change anything at the high energies without actually affecting low energy physics. So with all this, of course, we have the usual puzzle, and these are the ingredients of the typical puzzle phrased in semi-classical language. So let me try to go to the fuzzball paradigm, which was the next slide. So all you see with fuzzball is just very simple. Now you have a concrete theory of gravity, which is a complete theory of quantum gravity, we think, consistent theory. At weak coupling, you can just make brain-bound states, and I guess they are like normal quantum systems. But as you increase the coupling, you find that, at least in all the cases we can understand, the brain-bound state just grows in size and never really develops a horizon. So actually, for 2 charge extremal states, we can really follow this all the way from weak coupling to strong coupling. I think that's very interesting because it sort of makes the black hole much less mysterious for me. And as we know, we can do it for many 3 charge extremal states, some 3 charge non-extremal states. But the way I want to characterize fuzzball states is now if you try to draw the same little ball out here and you try to ask what's the state in that ball, that's nowhere close to the vacuum. So that's the only thing you can say. It can be very stringy, very messy, but this is the way I think of what fuzzball should be. So in all these cases, we just get a cap and we don't get a horizon. You could get if you ask about the infall question that people were talking about before, you can get this some kind of effective infall description for E much bigger than T, perhaps. I don't know if it is true, but at least it's allowed. But right now we're asking about Hawking quanta, evolution of quanta of energy T. And for those, I think you will be nowhere near the semi-classical evolution. So from very simple states, you can also actually get the Hawking emission. It matches precisely the value you expect for those particular states down to the last 2 and pi, but there's no information loss. So I think that's also very telling that these are very simple states, but you can actually get the emission and you can see where it's coming from. It's just coming from something like the surface of a star in the case of the fuzzball, and it is not made by pair production. So we just get the normal page curve. So, with all this, I'm just surprised that we shouldn't just jump up and say, we are done. I mean, the paradox only came, as far as I can see, because with black holes, we had a belief that there would be some kind of a no-hair theorem, and then you end up in the vacuum, and the vacuum produces the pairs, and then we don't know how to get out of it. But once you even have a few examples of how the no-hair theorem is actually bypassed, I mean, Nick Warner and Gibbons had a paper showing, how the various ways those things get bypassed in string theory, then actually black holes are like any other body, and we shouldn't try to make it more mysterious by trying to bring back the horizon. Anyway, so let me just put a last slide up here where I'll try to say this is just my view of why people would still like to make a picture with a horizon. And I think this is really goes to the heart of what I think about holography, which is a beautiful thing at the level of ADS-CFT duality. So there, if you have a large collection of D branes, and suppose you have a graviton falling on it, so then of course you can do the whole detailed calculation of it breaking into open strings, and that looks like the graviton got destroyed. But as the one showed us, it doesn't get destroyed. It's some very complicated but tightly bound special state of open strings, which is just like some kind of blob, and that slowly spreads. And whatever this blob is doing, you can map it one-to-one onto just falling smoothly into a geometry, which is just gently curved ADS, but actually there are no branes there. And so that really suggests that something very complicated can be replaced by empty space in some other description. And I think that is true, but we should not extrapolate that intuition to the black hole. Because if we do that to the black hole, okay, here's the black hole, we might think there's some degrees of freedom there inside. We want to think about them, but we are not sure what they are. But based on this, suppose we say that, well, maybe in some description, I could think of that like a vacuum. And so this is just my opinion here, but I think the holographic idea does not work at boundaries which arise from a volume, or from a surface, which is actually defined by the amount of entropy it contains. So we know a black hole has a particular boundary which we place at r equals to m, where that boundary, its area actually gives you how much entropy is in there. In the example which the holography worked very nicely, the entropy was 0 in the ground state. So when we have no entropy, you can replace something by a vacuum and get good physics out of it. But if you actually have entropy here, you have to describe that many states in the derivative description, and they can't all be replaced by the vacuum. So I think the difference between what we're seeing in the black hole and what we saw in normal ADS-CFT is that this is like a maximally entropic thing, and all those different states have to manifest here, and there they don't. So anyway, I'll just conclude with 2 questions I would like to ask the people who do work with wormhole. I would like to see if there's a simple bit model to understand the kind of pictures that have recently been made with those wormholes. I mean, I tried to make a few and they gave me strange results, but I maybe just not making it the right way. And then I would also like to ask if one can do a string theory calculation, maybe exchange of a graviton or a D-brane, the usual kind of calculation in string theory we know, where we don't see something as strong as you might expect in a black hole, but some very small, tiny effect perhaps, which shows us what's the meaning of saying that bits get non-locally identified, so that we can really understand from concrete calculations what kind of effect it is, which might be magnified more when we actually go to the black hole. Okay, thank you.
Thank you, Samir. Okay, and we'll now move on to Surat, who is the last of our panel members before we open up the discussion to everybody. Surat, you're still muted, I think.
Can you see my screen?
We can now hear you, but we can't see your screen just yet.
Oh, 1 second. Yeah. Okay, you can see the screen.
Okay, yes, it just came.
Okay, so thanks very much for this very interesting panel. The disadvantage of being the last speaker is I tried to modify my slides in real time to respond to some of the other panelists, and I hope I haven't made a mess of it. So I'll try and stick to time anyway. So I think we should separate this question of whether typical states have a horizon into 2 parts. One of them is we're an outside observer and you observe some star or some black object, and you make various probes of it, and the question is, does that lead you to infer that this object has a horizon? And the second part of the question is, if you take a rocket and you try and go into this object, do you have the experience that you would have at a smooth horizon? And I think these questions are slightly separate, so I'd like to just discuss them very briefly. So I think the first question about what you see from outside, I would like to argue that there's very strong evidence that you would see a horizon for a typical state. The evidence is, I think the argument is simple. And the first thing, as Jan pointed out, is that an observable outside the horizon is very strongly constrained just by statistical mechanics constraints, even without assuming something like the eigenstate thermalization hypothesis. And an observable, if you take an ordinary observable and you take a typical state, which is hard typical, it has to be exponentially close to the microcanonical ensemble. And we know what the microcanonical answer is because you can use the Euclidean theory or the conventional geometry to compute that. So a typical state just has to be exponentially close to that. So in particular, for instance, one such observable you could take is an observable that people have been discussing, which is at the conference, where you try and compute the energy gap about some state. So you could take a 2-point function of some operator, that's an observable of the kind I mentioned, and you could Fourier transform it over a time scale that's not exponentially large, but much larger than the entropy. And except for a free theory, the microcanonical expectation would be you would get an effectively continuous spectrum. And that's just in contradiction with the idea that you get a spectrum with gaps that are suppressed by power law. And so I think the fact that you get a continuous spectrum would suggest that you have a horizon. Now, Jan mentioned the question of an atypical basis, and I thought there's something we can actually say about that. And the thing we can say about that is that if you have an observable whose fluctuations are small compared to the observable itself, then not too many basis elements can be atypical, and there's a sense in which you can make this very precise. Now, in fact, we do have such an observable, and that observable is the metric, because you can not only compute the expectation value of the metric in the microcanonical ensemble, you can even compute the fluctuations of the metric just by using the conventional geometry. And those fluctuations are controlled by Hawking radiation. And we know that in the conventional geometry, the fluctuations of the metric are small compared to the classical expectation value of the metric. In such a situation, not too many basis elements can have an atypical value for the metric. And that's just a simple statistical inequality you can prove. And the reason is if too many basis elements had widely differing metric values, then you couldn't make the fluctuations work correctly. And so I think that you can't even get out of it by postulating there's a basis of states which all look very different and somehow average to the black hole. Almost all elements of the basis have to look very close to the black hole. And so you would suspect from outside that you do have a horizon. I think the question of the infalling observer is perhaps the real question about whether states have a horizon. Does an infalling observer experience a smooth experience as the person goes through the horizon? And Jan pointed out correctly that there isn't really a way to make that precise. But I think there's a pre-question we can ask. The pre-question is, can you at least find operators that correctly describe the experience of the infalling observer that you would expect in a smooth horizon? And then we could ask a second question about whether these operators are the correct operators to use or not. And the reason the question of existence is already interesting is because starting with the work of Samir and then AMPS, but also AMPSS, there are various paradoxes one can construct for such operators. And I just want to review where I think this question is. I think that if you allow these operators to be what are called state dependent, in that you allow the possibility that the experience of the infalling observer depends on the microstate, then you can avoid these paradoxes and explicitly construct these operators. But I think, although there's been a lot of discussion of state dependence, I think that some things we've kind of left behind as a community. For instance, Marolf and Polchinski pointed out that state dependence might lead to new paradoxes. And then I tried to argue that you couldn't see these paradoxes in simple experiments, but I don't think we've completely cleared out this issue. And I think that it's also too simplistic to say that we should just abandon state dependence. And that's because even though it's not commonly realized, one also needs state dependence if one wants to describe the interior of the eternal black hole. And so, this issue of state dependence, I think, is an interesting issue that I think we should think about more, which really describes the experience of the infalling observer in a big ADS black hole. The last thing I want to say is that I think there's a difference between flat space black holes and ADS black holes. And the difference is as follows. In flat space, black holes never dominate the microcanonical ensemble just because the Hawking radiation has more entropy. And if you think carefully about the AMPSS paradoxes, as opposed to the AMPS paradoxes and Samir's original strong subadditivity paradox, these paradoxes don't apply in this situation when black holes are actually atypical. And I don't know of any argument that interior operators must be state dependent for flat space black holes. And so I would suspect that, flat space black holes, there's no argument suggesting that there isn't a smooth horizon. Okay, so that's all I wanted to say. Let me just summarize and we can discuss more in the discussion. I think that from the outside, there's very strong evidence that typical states should definitely look like they have a horizon. For the infalling observer in a large ADS black hole, I think there are questions about subtleties with state dependence that I think we do need to understand better, even though they've been around for several years. For an infalling observer in flat space, I don't think there's any clear argument that there should not be a smooth horizon. And so I would suspect that there should be a smooth horizon. Okay, thank you.
Okay, thank you, Suvrat. So, and thank you to all the panelists. So we're now in open discussion for questions from other participants or comments. So I think everybody should have the ability to unmute themselves to jump in with any comments or questions. So please feel free.
Yes, can I ask a question?
Go ahead.
Yes, to go on with what mentioned, finished with, in both cases, whether in flat space or ADS, it seems that one can, for the infalling observer, one can use Kruskal coordinates, which means that the infalling observer in both cases will not see any horizon, but just see the singularity. So how does this argument break down?
So I didn't understand the argument. In Kruskal coordinates, you would have thought there would be nothing specific, nothing happening in the horizon.
Precisely. There would not be anything particular. So the infalling observer that is by definition that can use Kruskal coordinates is going to evolve, is never going to see anything particular happening, never going to see anything about the horizon, and therefore should not be able to see any state dependence that would tell them that they had just evolved beyond the horizon. If there was a space-like singularity, they would hit it in finite proper time. If there were a time-like singularity, they could avoid it. So how does this expectation break down, and how does state dependence for ADS black holes enter the picture?
Sure. Let me just answer briefly, and maybe the state dependence is designed so that the experience of the infalling observer doesn't actually change with the state. So it might sound slightly paradoxical, but the state dependence is designed so the infalling observer has the same experience in all microstates. But it's nevertheless true that the operators are in some deep sense state dependent. But I mean, the whole point of setting up these things was to set up a configuration, set up a scenario where all observers would see the same smooth horizon in all states. So the state dependent picture does not predict that there's something special happening at the horizon. It's the fuzzball picture, which I think, Samir should feel free to correct me, that I think would predict something special happens at the horizon.
Just make sure. I want to just make sure that I got it. That I got what I understood, what I thought I expected.
But also I think at extremal horizons, the story is quite, I mean, at least in ADS2 there is clear. I mean, I don't know if there's any argument for, I mean, all of Suvrat's arguments are very nice, but, you know, they had to do with finite temperature and, you know, all the ideas of eigencentralization. And I mean, all these things are basically finite temperature. So I think there are two questions which are important to understand. First of all, do extremal black holes have horizons? Do extremal horizons exist? Or are the extremal solutions to the horizon just garbage? They have to be thrown away. And the real solution are the fuzzballs. That's one question. The other question is non-extremal, finite temperature. Then, okay, we can discuss interior operators and so on and so forth. But I think there are two questions which I think it would be good to have to put in two different boxes and to answer. That's my.
Let me point something out about the extremal black holes, right? So there was this paper by Dabholkar, Gomez, and Murthy, where they computed the entropy of a black hole, including new geometries. So they started from ADS2 and some other geometries that would contribute. And they found, well, with certain assumptions, they found that e to the s was some set of integers, right? So this, to me, shows that we should take seriously the ADS2 for understanding the extremal entropy, in the sense that it's a calculation based on ADS2 logic that gives us precise answers, right? Gives us the actual degeneracies. Now there might be another picture where there are caps and there are other solutions and so on. But it might be that there might also be a duality between that picture with the caps and the solutions and the ADS2. But I think it's too extreme to say that the ADS2 is wrong.
No, it's just that it's not dual to a pure state. I think this is the argument. I mean,
well, it could be that, yeah, so it could be that it is an entangled state of the ground states of one CFT and the ground states of another CFT.
Sure, absolutely. So, I mean, if you think about an ADS2 to boundaries, and, then indeed, I mean, that's very kosher. But, if you just want to think about, classical 1997 holography, you have one boundary, you have a Poincare ADS2, and the question is that there's a boundary 0 plus 1 dimensional CFT. That 0 plus 1 dimensional CFT has some ground states which break conformal invariance, and you can argue again using this 0 plus 1 dimensional CFT arguments that the Hamiltonian basically is 0 unless that CFT doesn't have any conformal invariant ground state. So somehow using just pure ADS CFT arguments, you can throw away the Poincare ADS2 as a pure state. Maybe it's something else, absolutely. But I think what fuzzballs are, I mean, if I understand correctly, what the fuzzball proposal says is that the classical black hole solution is not dual to a pure state. The rest, whatever is dual to, can be some nice mixed state, no problem. But I think the way to define the fuzzball proposal in the cleanest way is to just say that the classical textbook black hole solution is not dual to a pure state. And I think in the ADS2 case, I think that's.
But do you want to restrict the proposal to only extremal black holes? Because for extremal black holes, there's, of course, just a the following semi-classical argument. You could think of extremal black holes physically as taking a near extremal limit and then going towards extremality. And then just cosmic censorship would put some singularity at the inner horizon, which the infalling observer would hit in a proper time that goes to 0 as you reach the extremal limit. So, I mean, the fact that extremal black holes don't have a good interior might be something that you might be able to argue for even in other ways. But presumably you'd like to say something about real black holes, not just about extremal black holes.
If I can do extremal, then I can do near extremal. So I'm a very insidious person, like a politician. You give me a finger, then I get the whole hand. So if I can do extremal, and if people concede that extremal black holes are replaced by horizonless configurations, capped horizonless configurations, then I'm quite insidious. So I mean, you can look at the Penrose diagram, for example, of a near extremal black hole. If the extremal black hole is replaced by the horizon in this garbage, then the near extremal ones also have to be replaced by horizonless configurations. And
the argument I gave doesn't generalize, right? The argument I gave was just that you have the inner horizon is unstable. And because when you take the near extremal limit, the infalling observer crosses from outer to inner horizon in infinite proper time. There's something special that might happen as you go to very near extremal black hole. But that doesn't generalize if you have a big black hole or Schwarzschild black hole. So it's not like, I mean, in an extremal black hole, it might be there's something bad behind a near extremal black hole. There's something bad just behind the horizon.
But
just because of strong cosmic censorship.
That for an extremal black hole, the singularity is always time-like. And in fact, if I were to take Reisner and Nordstrom, whether it's extremal or not extremal, the singularity is time-like, whereas Schwarzschild is space-like.
So there's actually some work showing that as Subrat said, the inner horizon is unstable. So that if you send in some perturbation and then you probe it sometime later, because of mass inflation at the inner horizon, the second probe goes in and measures a null shock wave at the inner horizon. This is a very nice calculation of Meralf and Ori about almost 10 years ago. So, so it's not clear that the region behind the inner horizon is anything more than a fiction of an unstable classical solution. And then, of course, when you go to extremality, the inner horizon and the outer horizons coalesce from the point of view of externally falling probes that fall from some fixed height. So it could be that extremal black holes indeed have some sort of null singularity at the horizon that would be explained by some sort of stringy, fuzzball configurations. And then the question of what happens to that picture when you go away from extremality, of course, is the $64,000 question.
Could I make a comment on what Juan was just saying about the ADS2? And you can use that to get very good partition functions, which are so accurate. And Ashok-san also uses that for ADS3 to get very exact entropies. So the way I always thought that Ashok-san's program should be understood is that even though he writes the Lorentzian metric, let me think of it as a Euclidean metric, and then I indeed do want to take the limit, as Surat was saying, from T positive down to temperature 0. And then certainly in that channel, if you look at so it looks to me like an extension of the Gibbons-Hawking way to compute entropy by looking at the partition function, the one loop partition function. And that's why I think Ashok-san's answers work beautifully. It looks Lorentzian, but I think it's just the analog of the Gibbons-Hawking calculation, because the metric looks the same whether you do Lorentzian or Euclidean for what he's using it for. On the other hand, if you then ask what are the states which are actually running around the loop to give rise to that partition function, I would say that they have to be fuzzballs which do not have a smooth horizon. So I would take everything that Ashok-san is doing from the horizon and outwards and say, okay, if I just take T to IT, well, it's all correct and it's Euclidean. But then if I go past the horizon to look inside, that's where the caps are. So I would say in the Lorentzian section, all the solutions are the ones with these caps. But then if you try to make a one loop path integral and try to compute the path integral of all these guys running into a loop, that path integral can have a saddle point, which you can then compute in the cross channel by the disk diagram, which saddle point, of course, as we know, just ends outside the horizon. And what Ashok-san and Dabholkar are doing is doing a much more detailed calculation of that saddle point to all orders, while Gibbons-Hawking had only the leading answer. So I think that's the way I understand the relation between what Sen or Dabholkar might be doing and the fuzzballs.
But I mean, as we said, the Euclidean solution is giving us information because it's telling us about the microcanonical average. And even if it's a Euclidean computation, but then we're not allowed to have, like, as we said, very different basis elements that all add up to the same average. And the reason for that is we can really compute fluctuations of some quantity, and those fluctuations are small in the Euclidean theory. So I think this idea that we have very different basis elements and they all average out correctly, that's not consistent with the fact that the fluctuations in the Euclidean geometry are also small.
Right. So I think I didn't quite understand, because I don't think the fluctuations have to average out to give the black hole traditional diagram inside the horizon. What I was saying is a little bit more like this. If you just take 2D CFT on a torus, which is, let's say, very long in one direction, then if you look in one channel, a lot of different states are contributing in the channel, which has got a small circle and therefore a high temperature. But then in the cross channel, the vacuum propagates, and I can get the same partition function by equating these two, how we get the Cardy formula. So I think when we look at the Gibbons-Hawking calculation, we are looking in the channel where just having a disk and replacing it by the vacuum at the horizon just gives the entire answer. But then in the other channel where you see everything circulating around in the Lorentzian section, you will actually see all the actual microstates. So I think the disk calculation is a little misleading because it's the other channel. Because again, in the torus computation of a partition function, because for a long torus, you could just get the entire answer by just propagating the vacuum in one of the two directions of the torus. It shouldn't make us think we should just think of the vacuum also in the other channel. The other channel has a huge number of states. So I'm not saying that you should actually be able to average the fuzzballs to get a smooth interior for the black hole. So in terms of what Subrat was saying, what should an infalling observer feel? So with this whole fuzzball complementarity thing, what we were trying to see, and again, I don't know if that is correct, whether we can get fuzzball complementarity, but it's at least allowed by everything that we know. And what is allowed is that if you look at objects with E much bigger than T, the vibrations of the extra degrees of freedom created when you fall onto the fuzzball, well, they are not entangled with anything else, so they don't suffer from the AMPS argument. And the evolution of these extra new degrees of freedom that come in when E is much bigger than T, their evolution can be mapped in the ADS-CFT kind of idea to smooth info. So that was the idea of fuzzball complementarity. Just again trying to do ADS-CFT, but the new degrees of freedom which are coming, they're not entangled with anything, and they bring new degrees of freedom, and the evolution of those degrees of freedom could be like ADS-CFT. But I think the Hawking puzzle really is not about E much bigger than T, and therefore not about the infall question. It's about the quanta with E of the order of T, because they are the ones that create the problem. And I think they cannot be understood by using a geometry around the horizon, which is smooth in a ball around the horizon. So I think I would really like to ask maybe the other people in the panel or anybody else who wants to comment, what would they say about the evolution of the E of the order of T modes around the horizon? Is the horizon really a vacuum region? can I really get that evolution of low energy modes? And if not, well, why not? Because if you give me a smooth region there, any picture, I could use it to get the evolution that Hawking was using. So maybe that's a question to.
Sorry, but can I just understand correctly? It's very, the simple question is, let's say I really think of a low energy observable of the kind Jan was talking about. The observable is I take the metric and I average it over the horizon, or maybe I average it at twice the Schwarzschild radius. That's a low energy observable, I think you would call it. Is the claim that this averaged observable will differ appreciably from the conventional black hole geometry, or that in some basis of states? I mean, I'm trying to understand what the claim is.
Okay, let me understand the question. At twice the Schwarzschild radius means you're looking at a geometry of a surface far outside the hole.
Yeah, or you can make it as closely, like you can go to 1.1 times the Schwarzschild radius, or I just want an answer in these terms. Let's take the metric and let's smear it out over some region, and let's have an infalling observer who measures this physical quantity, which is the metric, in some gauge. Okay. What is the claim? That this person will see a difference from the conventional black hole geometry, or not, in a typical
So
state?
I think there are a few different aspects of the question I just want to understand. So if the observer is at 1.1 times the Schwarzschild radius, my prejudice is that all the corrections which are coming from fuzzballs, generic fuzzballs, are very close to the Schwarzschild radius, maybe even a few Planck lengths. So at that place, all the individual states, all our generic states are all roughly the same and have the standard Schwarzschild metric. So there he should not see anything. As he comes in, now again, if you have an observer, I think the main thing is to ask, how does his degrees of freedom interact with the fuzzball? So you have to tell me that the observer, I guess if he's a small guy of size much less than the size of the black hole, he is a guy who carries E much bigger than T.
I have number of observers. So my observers are going to be spread out over the Schwarzschild radius, and they're going to later combine their observations.
Very good.
So the question is, so the physical quantities, I take the metric and I literally average it. I integrate it over some sphere of radius R, where you can take R to be whatever you like. And now the question is this observable, which I think is a low energy observable, is this observable supposed to be appreciably different from the Schwarzschild geometry or not?
Right. So I think I'm puzzled by why one would call this low energy for the following reason. The main issue with fuzzballs in trying to observe them is that we know that the energy gap is the mass of the black hole divided by how many states we have. So it's a fairly small energy gap. Okay? You also talked about this in many papers. So the moment you probe a system with the energy which is more than the energy gap, you can't actually probe the particular state you started with. You'll immediately jump into a whole band of states. Right? So what's going to happen when the observer comes in is something like a Fermi golden rule kind of evolution. You start with one state, but you actually immediately spread it over a whole band. And the kind of models I was making for the fuzzball complementarity was that as something goes and spreads into a band, the way the wave function spreads over a band is pretty universal and doesn't actually care about anything more than the band spacing. But all this doesn't actually probe the state that you had, because the state has already jumped by the energy which came in. So I wouldn't call this low energy because it's jumping the state to other
Please give me
states.
another observer. Now the question is, what is the low energy observable in Jan's terminology, which is comprised of the metric and maybe some low order polynomials of the metric, that will allow you to determine the difference between a fuzzball and the black hole geometry? Is there such a low energy observable? I mean, and if so, what is this observable?
I think so. I think there are no easy observables, but in principle, if you sent in a wave with a very long wavelength, you could even use a wavelength much bigger than the radius of the black hole. And if you did soft scattering of this guy and kept collecting it multiple times, so like, if the black hole is made of 1,000 Planck masses, and you send in a quanta of very long wavelength and you scatter it off like 1,000,000 times, after some time, by collecting all this data, I think you should be able to distinguish one fuzzball from another. But you may have to, because the many quanta will be coming out of the fuzzball, the non-extremal fuzzball, as radiation, until you collect almost as many quanta as radiation would have emitted, you wouldn't be able to see the difference. So I think when you try to observe differences by looking at just one or two quanta, you run into the same problem which you find in trying to distinguish whether this particular room right now is in a pure state or an entangled state. By looking at any one local observable or any one atom, you can't tell. But that's the property of any statistical system. It has nothing to do with black holes. So when you say, how do I measure? Actually, that question, I think itself is not taking you anywhere near the puzzle you're trying to solve, because the question is equally strong even for the gas in this room. That's why I wasn't actually understanding the question.
No, but exactly. I guess the point is, what is, if the claim is that you need to measure an exponentially accurate quantity, then I think we're not speaking of geometry in any meaningful sense, or you need to measure exponentially large number of quanta. The precise question is there any low energy correlator, any correlation function of the metric or low order polynomials of the metric that the fuzzball proposal predicts will be different from the conventional geometry?
I think there should not be, because if there were, then you wouldn't, for example, be able to get fuzzball complementarity. I think the whole difficulty here is where I'm maybe changing your starting point. I don't actually like to talk in terms of endpoint functions, which are very standard in particle theory. But I think endpoint functions do not ever bring us close to the information puzzle. And that's why the way I was phrasing it was always talk in terms of states and not endpoint function correlators. So let's ask the question in the way that I was posing it there. Is it a state in a ball-shaped region around the horizon, the vacuum to leading order? That is the dot product of that state with the vacuum close to 1 or close to 0? That's the only sense in which I can define the distinction between a fuzzball and the traditional hole. If you ask, is the two-point function the same between the vacuum and a typical fuzzball? Just because of randomness, you will always get the answer should be yes, because a two-point function in this room also can't tell me the state in this room at all. It can't distinguish one state in this room from another state or a pure state from a mixed state. So that's a fault of trying to use finite point functions for any large system. But let's talk in terms of the state at the horizon. If that state is close to the vacuum, you already start in the information puzzle, and then you need non-local correlators of identification of bits and wormholes the way many people have been developing. And I think those take us to real questions about what we should do to resolve the information puzzle.
But I don't think.
Okay, sorry, Suvrad, I'm gonna. Sorry, everybody, I'm gonna interrupt you guys because Emil has a hand up, and I want to get some more people in the discussion. So thanks. It's all very interesting, but let's have something from Emil.
Yeah. So I wanted to back up a step, because a lot of the discussion is about what's going on near the horizon and experience of infalling observers and so on, and just ask a very naive question about what do we mean operationally by the horizon. So certainly in classical geometry, there is such a notion, but then if you try to think quantum mechanically, you have to ask, okay, what observable am I going to concoct which measures the causal structure near the Schwarzschild radius? And so I think this gets to Samir's point about, if you look at observables that have E much bigger than T, then their back reaction substantially modifies the causal structure near the horizon because of the butterfly effect. If I'm talking about very low energy observables, then they could be strongly affected by the thermal fluctuations at the horizon. So when we ask the question, does a black hole have a smooth horizon? I have just a very naive question. What do we mean by that in the quantum theory of gravity? What is it that we're calling the horizon, and how do we operationally determine what it is, where it is, what its fluctuations are?
May I?
Stan, go ahead.
Ask something relevant,
Mm-hmm.
perhaps? Well, classical for the horizon isn't. But on the other hand, quantum mechanically, I would guess that the horizon is present by the fact that a quantum field theory in the presence of a horizon does not have a unique vacuum, and therefore, by measuring the degeneracy of the vacuum state, it might be possible to say something about how important, how significant the effects of the horizon may be. I don't know. Because that's how it differs from the gas in the room that Samir was mentioning. The room is in a flat space-time locally, so the vacuum there is unique. As we go near quote unquote the horizon, because of course the horizon isn't a place, the vacuum of the quantum field theory is not unique. So a quantum observer is not going to be able to say which vacuum state they're talking about. I would venture to propose.
I mean, a related thing will be that one expects, if we expect all the information to come out in the Hawking radiation, then we are not saying that this horizon, whatever it is, represents a strict causal structure in any sense. So I agree one should maybe try to sharpen how one should define a horizon. For what physical processes should we think of there being a horizon, and in what approximation is it valid? And
I'd kind of like to bring the discussion back to another very simple point, which was raised by Samir, and perhaps those people who think that the black hole has, or typical states have horizons. What's wrong with Hawking's calculation? Where, and I mean that in the sense of Samir was talking about, what's the bit model of what you would have that you would use to avoid the information paradox, and tell me what's wrong with Hawking's calculation locally at the horizon? Are you going to invoke non-locality, or what?
Well, the idea, I think the idea is the current idea is that the semi-classical physics is correct to describe the state at least semi-classically, and that in order to get the information out, you really need to do non-perturbative. You need to get the state outside using non-perturbative accuracy in the gravity theory. Right? Now, there is a tool which is this Ruta-Kayanagi formula, right? And the Ruta-Kayanagi formula tells us a little more, which is it tells us which region of the space-time we should assign with particular quantum degrees of freedom, right? So we talk about, for example, the black hole entropy, like, for example, Samir was talking about the entropy and equal to the area or not. That, if it is so this entropy is computed, the fine-grained entropy is computed by this Ruta-Kayanagi formula, and this surface could be so this surface could be trivial, in which case the black hole degrees of freedom cover everything, or it could be non-trivial, in which case the black hole degrees of freedom only cover a little region behind the horizon. And one of the things that people discovered last year, so Ahmed and company and also Pennington, was that for an old black hole that's been radiating for a long time, the surface is just a little bit behind the horizon. So most of the interior should be viewed as degrees of freedom that belong to the radiation.
This is okay. Go ahead.
Okay, so you could say, so then when you compute the entropy, if you apply the proper sort of Ruta-Kayanagi formula, then you would get the entropy that is consistent with unitarity.
Okay, this is a sort of debate for tomorrow, I think, but you know, to some extent, we kind of knew that 30 years ago, in the sense of, we know that there's an awful lot of entangled particles inside the black hole, which perhaps sit on some kind of Cauchy hypersurface, and that I'm going to call the island. What does it tell us that's new that this formula tells us? Yes, there's a whole pile of stuff that's inside the black hole, it's entangled, and will purify the stuff outside the black hole.
Well, first of all, this formula is derived from gravity. So it tells us the gravity rule for computing entropy. Now, you might not like it, you might say whatever, but it's a formula that wasn't there 30 years ago, and now it's there, and you can apply it to this problem, and it gives you a result consistent with unitarity. You might say, well, it gives me a weird answer that I don't like. So, okay, it's true, it's weird.
It's also Euclidean quantum gravity, yeah.
What?
It's also Euclidean quantum gravity.
Well, Euclidean Lorentzian, I mean, you use Euclidean to prepare the state, but you could evolve in Lorentzian signature. Yeah, it's
bring the conversation
methods, but yeah, it's in the same. I think it has the same status as Gibbons Hawking. So it does not give us the explicit degrees of freedom. It's just, if you don't like Gibbons Hawking, then you won't like this.
No.
If you like Gibbons Hawking, then you cannot not like this one. So
I think this is a debate for tomorrow. I think I'd like to focus back on the horizon issue, and really, if you buy that picture, what's wrong with Hawking's calculation, which is a local calculation involving bit models at the horizon where we think there's a vacuum? What's wrong with that calculation?
Can I try and say something about this question? I think that you know, there are two issues. One of them is, as Juan is pointing out, if you just look at the calculation outside, then Hawking's calculation is not precise enough because it doesn't take into account non-perturbatory effects, which are enough to just purify the radiation outside. But I think the point that Samir and so on has made, I mean, Samir made this point very powerfully many years ago, is that you also need to consider the inside to really get a paradox. And I don't think anyone, I mean, I don't think in these new island developments or in the picture of complementarity or the picture that Kyriakos and I had where the degrees of freedom inside were scrambled versions of degrees of freedom outside. In none of these, I mean, in all of these, it's true that the true wave function is not given by an entangled wave function of some independent degrees of freedom inside and degrees of freedom outside. So if you're saying that there are corrections, large corrections to the true description of the wave function, I don't think anybody would disagree with that. But I don't think that tells us that you don't have the black hole, because the black hole is a question about what a low energy observer sees. I mean, when we say that the gas in the room, or, you know, the photon gas that was used to develop quantum mechanics was thermal, we know that the true density matrix of that photon gas is completely orthogonal to the thermal density matrix, because you change some very small degree of freedom and it'll make something completely orthogonal. But nevertheless, the thermal density matrix is a great description for all normal questions you would ask. And I think that's the picture we have for the black hole as well. That it's true that the true wave function, the true degrees of freedom are not given by the semi-classical bit inside, bit outside. But for all effective purposes, you go and you measure the metric, you see the black hole.
Yeah, but then if I do that, I do the Hawking pair creation. I've got a very old black hole, and it's extremely, but does it look like a black hole that I see that's newly made? And does it Hawking pair create, or is there some non-local effect of some wormholes, or what are you trying to sell me here about how you change the calculation?
No, non-local effects is not a postulate. I think with Samir is something, I mean, you know, you can, as one of the things I tried to do sometime back, and it's easy to check, is that in empty space, you can see this identification of bits in one point and a complicated combination of bits far away. And this is something that just follows by just taking semi-classical gravity and following your nose. So this is not some additional postulate that we need to put in. I mean, we were discussing this a couple of days ago in the conference when we talked about the Hamiltonian being a boundary term. So I think
so Red, I'm just going to bring in Eric, who I see has his hand up. So Eric, please feel free to go ahead.
Yeah, I want to support Sufrat in this picture, actually, that even if you accept the fact that you take the first Paul proposal, I mean, so there's no horizon and there's something like behind the horizon, you still would eventually like to get a semi-classical picture where the black hole radiates. So it will radiate certain particles. And then you may ask the question, what is left behind is the state of a black hole in a different state. And that different state actually is correlated with the state of the radiation that came out. So there is some entanglement between the particles that have been emitted and the black hole states. And what actually happens now is in this island story, or even what Sufrat and Kyriakos have been doing, and actually also with Herman, I had a similar proposal, is namely that you indeed use this entanglement between the radiation and the black hole to construct something that looks like an interior geometry, or at least interior modes. So we have first, so indeed the Hawking picture that there were independent modes behind the horizon is wrong. It's precisely the fact that those modes are not independent from the degrees of freedom that we had on the outside is what is changed in this current story. And that's also how this information eventually can get out. So there's no independent set of modes that are not related to the radiation that has come out. And in the island picture, that is even much more explicit, because then you need the radiation to reconstruct what's inside. So that has certainly changed, and that's not something that Hawking did when he did his calculation.
But what's the mechanism by which that information gets, I'm sitting in front of an old black hole and I've got a Schwarzschild metric. Is it pair producing a la Hawking, or is it, how is the information about the bag of gold inside getting out?
You're going back to this question of how does low energy affect the field theory on nice slices breakdown, right? I guess.
You're asking me, or
Yeah, I think in this field theory description it does not get out, but if you allow non-perturbative effects, wormholes and so on, then it gets out. So
okay. I certainly buy that you can purify the state with lots of wormholes between the inside and the outside. I'm just looking for something a bit more precise in that description of what that wormhole is. It sounds like you're redefining the problem. You've just replaced the word with the entanglement on a bunch of particles on a good slice inside the black hole. That entanglement's now just been called a wormhole, but it's the same problem. You just redecorated the problem.
I think I have in mind something like what the discussion of a PETS map that the Stanford group had. I think that's a very concrete idea. So the idea is you are going to do a very complex operation on the outside, and it's so complex that this operation creates a wormhole that makes a traversable wormhole that somehow puts out the information. That's the picture that they proposed, and they showed how, in the context of a very simple toy model, how that works. If you do a simple operation, then you don't see the
if somehow you mystically say, I can get all the entanglement data from this stuff that's inside, somehow outside, it sort of sounds like you're just redefining the problem and saying, look.
It's not a redefinition. It comes from doing a calculation. So they showed what calculation you would need to do. And
but
in
the
very simple model, they actually did the calculation.
How is this different from any complex quantum system where I've prepared some very delicately entangled state over large space-like distances? And so if I did an extremely complicated quantum computation over, in some quantum computer far away, it would magically change the state in the room where I'm sitting.
No, that won't happen. If you act
how is it different from that?
It's different because if you act with a unitary on your computer, it will not affect the system far away. In this case, if you act with a unitary on the radiation, it can affect the region behind the horizon.
Yeah, I agree with that, what Ahmed just said, but I think that there's actually a simpler example, which I think is not appreciated enough. I think maybe the question that Nick and others have is that they're worried that these are all very complicated operations. But if you give me a slightly simpler problem, you can actually do something even in perturbation theory. It's something that Kyriakos discussed some time back, and it's very concrete. So the problem is as follows. I take a state that's close to an energy eigenstate, and then I throw in a shock wave. I throw in two different kinds of shock waves. And now the challenge is I'm sitting outside and I need to figure out which kind of shock wave was the one I threw in. And both of them had the same mass, but they had slightly different distributions. And of course, classically, you cannot figure out which one it was. But quantum mechanically, you can, because when you look at the fluctuations of the Hamiltonian, of course, is the same in both theories. But if you look at the fluctuations of the Hamiltonian, and if you started with an almost energy eigenstate, which had small fluctuations, by looking at the fluctuations of the Hamiltonian, you can figure out in perturbation theory what the form of the shock wave was. I mean, this is something you can do concretely and doesn't require any additional assumptions. So already quantum mechanically, the black hole horizon is more porous than it was classically. Now, you're right that in this, I had to give you a prior. I had to tell you that, I had an energy eigenstate, and then it was a simpler problem. I was just asking you to differentiate between a few different kinds of shock waves. So I can't use perturbation theory to determine the microstate. But already this perturbation theory kind of tells you how information might start to come out. I think this is, can be made very concrete.
Okay, and let me just
ask a question to some of the panel.
Yes, Samir, just before you do, Samir, just let me mention that we're just coming up towards our end time, or even slightly over. I'm happy to continue as long as anybody else is.
You are a faculty postdoc, so you know the rules.
I know the rules, and I'm just wanted to let everybody know I'm not going anywhere anytime soon. But if we want to set a timescale, that's fine by me too.
We should probably wrap it up in about 15 minutes, but the conversation's going, so let's just keep it going.
So far, so good. So please continue, Samir.
Okay, so I just wanted to ask some of the other people who were talking about wormholes and so on. So from what I understand, if I burn a piece of coal and I collect the photons coming out of it, and on the other hand, I make a small black hole and evaporate that, and I collect the photons coming from it. Is there a difference in the two stories? From what I understand, maybe from what Ahmed said right now, there is a difference, right? Because if I try to do a unitary on the photons I collect from the piece of coal, it would not flip the atoms which emitted the coal, which are entangled with these photons, so that it wouldn't change something in the other room, as Emil was asking about. But on the other hand, for the black hole, if I do a unitary on the radiation, it would change something in the black hole. So do I understand right that you would like to say there is a difference between the black hole is somewhat different as an object? It's not just like a piece of coal. And the second part of that question would be, well, at least for very simple things like the two-charge extremal hole, we can start at weak coupling, where we just have strings which are emitting, gravitons. It looks like a piece of coal to me. And then as I increase the coupling and it sort of goes towards a black hole, if there is indeed a difference between the coal and the black hole for you, how does the difference set in? Why does it set in? And is it only when the gravity somehow becomes strong that this kind of difference sets in and the wormholes appear? Maybe some clarification on that would be great.
The comments I can, okay, yeah, so the comments I would make would be, from the outside, the black hole and the piece of coal would be indistinguishable. Well, I just mean they're both going to evaporate normally. But the difference between the coal and the black hole is that the black hole has a horizon. And the statement that I was making is about understanding the physics behind that horizon, not the physics as it would appear from outside the object far away. That's my distinction.
But wait, the unitary is on the radiation outside. I'm just trying to understand your statement.
I think that one important thing is that in the new developments, there was a different perspective in how we build the interior, right? So should we assign the interior to some mysterious black hole degrees of freedom, which was something we could have thought, or should we assign the interior as a property of the radiation? So the difference perspective has been in the description of the interior.
So in a piece of coal, you would not make the same kind of
yeah, there would be no interior in the piece of coal. So we don't have an interior, so the problem doesn't arise.
So how does a small mess of strings, maybe just a bunch of 20 strings, that looks more like a piece of coal, right? But as I slightly warm it, it starts becoming towards the black hole, then this new kind of physics sets in. Can you just show me some continuity between a small bunch of strings, which is like coal, and maybe a larger bunch of strings, which is like a black hole?
I think the continuity is not hard to see. It's the following. I think that these quantum gravity effects, you're right, of identifying degrees of freedom in one region with another region, if they exist, they have to exist everywhere. And as I said, you can examine them in empty space very carefully. But I think that the difference in the piece of coal and this situation is as follows. To measure the black hole information, you need to measure an S-point correlator. And S happens to be m Planck divided by e to the power d minus 2, where e is the typical energy scale of the Hawking quanta that you're collecting. And so you can't consistently take a limit where m Planck just goes to infinity and you keep e constant, because you need to measure a higher and higher point correlator in that. The coupling constant of the theory is e over m Planck, and the correlator you need to measure is m Planck over e, is the inverse of that. So there's no sense in which you can decouple quantum gravity effects for a black hole. On the other hand, for a coal, you can keep S constant and take m Planck to infinity. And then of course, you don't see any quantum gravity effects. You can just forget about all of them. So the fact that these effects are important for a black hole and they're not important for coal is just for this reason. I think that in one case, you can take m Planck to infinity while keeping S constant. In the other case, you can't.
Okay, good. So I think all of you are saying there's some difference between how coal radiates and how a black hole radiates. Somehow the quantum gravity somehow comes and changes the picture. And so I guess when I start with just a bunch of 10 strings at weak coupling, it's more like a coal. As I increase the coupling, the physics starts changing because quantum gravity somehow gets in and the wormholes appear. I'm just trying to get a picture.
It could be that if you have a piece of coal that is very complex, like it's not coal, but it sits in someone's lab and very complex state, very carefully designed Hamiltonian, then it will have an interior also. So
I think Jan wanted to say something.
Yeah, the dual description of black hole formation and creation in the gauge theory is, of course, a conventional coal-like process where you shoot some crap together, you create a deconfined ball of plasma in QCD, which then evaporates again. So from the dual point of view, it's kind of a coal-like process, but it has a very large number of internal degrees of freedom. And the key transition is whether you stay in the confined phase or whether you make a deconfined plasma ball. And it's pretty hard to access those internal deconfined degrees of freedom while you are a confined observer. But in some sense, there is a conventional dual picture of black hole creation and evaporation in holography.
And maybe I can add to that. Maybe I can add to that by translating maybe what Juan was saying a moment ago into the language Samir was looking for. So I think, imagine, Samir, you have a scenario where bound states in string theory are fuzzballs, but that they are extremely absorptive, and that an infalling observer, at least for some regime of validity, experiences effectively a smooth horizon. Then I think Juan was saying that in that situation, your description, your approximate effective complementary description of the interior of the black hole should emerge from the string theory bound state. Whereas if you have a separate distinct scenario involving wormholes, these interior effective degrees of freedom would be associated instead to the radiation far away rather than to the bound state of the black hole itself. Did I translate correctly, Juan?
I think so. I think that what takes the interior to the radiation is the fact that the interior is entangled with the radiation. So that's what happens when you have entanglement or non-zero entropy for the black hole degrees of freedom. Very high entropy.
And Emil,
I could take a black hole with as much entropy as the coal, right? I mean, a black hole of 1,000 Planck masses may have much less entropy than a piece of coal which has 10 to the 23 degrees of freedom.
Yeah.
But you're saying till I increase the coupling to make the coal more like a black hole, there should still be no wormhole, etc. in the coal, even though it has more degrees of freedom. It's not just a question of number of degrees of freedom. I guess it's also the coupling or the density of them that's important to you.
It's also the energy of the radiation, right? In the case where you took the black hole, which had much smaller entropy than the coal, the energy of the radiation is going to be very high. So the correlators you're measuring, so I mean, it's again not surprising that Planck effects would be important.
Okay, and Emil wants to jump in.
Yeah, so I just wanted to understand this point a little bit better. So, so if I understand correctly, you're saying, okay, that if I have a lump of coal and I've collected all of the radiated photons, I have the ability to do some unitary and it won't change the state of the lump of coal. Whereas if I have a black hole, whatever I do to the radiation affects the black hole interior. So,
but
it sounds to me,
not its exterior. Sorry, not its exterior.
What do you mean not? What? Sorry.
So it can affect the interior, but not the exterior of the black hole. So what we normally think of black hole degrees of freedom are the degrees of freedom of the black hole as seen from the outside.
But if I'm thinking about this in some Hamiltonian terms, it sounds like you're saying that the difference is in the lump of coal, my Hamiltonian is basically factorized between the remaining lump of coal and the radiation far away. And so I can execute unitaries that are acting only on the tensor factor, which is the radiation far away, and leave the coal untouched. Whereas you're saying the situation in quantum gravity is very different, that whatever operations I have available to me don't factorize between black hole interior and far away radiation.
Yes.
And so you've introduced some element into quantum gravity which is highly non-local. So the thing that Samir, for instance, in his talk was not admitting as a possibility in his proposal was the idea that the degrees of freedom of quantum gravity are somehow highly non-local, and so by the time the Hawking photon gets, m cubed distance away from the black hole, it can't affect what's going on at the horizon anymore.
Yes. Yeah. That's a key point there. there is a non-locality in that sense. Yeah.
So, but I mean, I want to emphasize once again that it's not something one introduces as a postulate. It's not that one postulates this to happen. It's something that you can examine. And as I said, I think you can examine in simpler situations as well. And I think maybe one more difference, just to emphasize, is the fact that the unitary you need to do on, if you look at how complicated it is in terms of simple operators, the unitary you need to do on the Hawking radiation it's a very complicated unitary. It involves some order S operations in terms of simple operators. And that's in the real world, probably if you did that with the radiation from a coal, you would again see this identification of degrees of freedom in one place and the other place, but you would never usually do that because the complexity of the lump of coal is just much lower. I mean, that S doesn't scale with M Planck. So you usually just take some limit where you just see local physics and you don't see these effects.
So my takeaway here is you're saying, okay, I was moaning about the fact that how you correct the Hawking calculation. You're telling me that there's a non-local effect that somehow connects the Hawking quanta that are far from the black hole to the stuff that's inside. And this is some part of quantum gravity that we as yet haven't described, but is somehow captured by this replica wormhole. Is that correct?
Yeah, that sounds reasonable. Yeah, replica wormholes are some aspect that appears when you compute a complex observable such as the fine-grained entropy.
Absolutely. Yeah.
For other complex observables, you'll have other geometries.
But do we have any way to calculate a priori what these non-local effects are? Or do we just simply say, oh, they have to be there to purify the Hawking radiation and they are whatever they have to be to do that?
Well, you have to decide what you are computing first. And then we currently don't have something that works for any computation. So for a very specific computation, which is the computation of the fine-grained entropy, then you have very specific contributions, which are these replica wormholes, which show this non-locality. They connect the radiation with the interior and so on.
Maybe I would like to differ from that. I think we do. I think in some situations, in many more situations, I think we can also ask what these effects are. As I said, one example would be you take empty space, make an excitation in the middle of empty space, just act with a unitary in the middle of empty space and ask me to read off what the unitary is far away. Mm-hmm. And I can tell you what that would be just in semi-classical gravity, what you need to do far away. And in local quantum field theory, that would be impossible. And as I said, we can I'll talk about it maybe day after tomorrow, but it's something one can do quite concretely. And of course, this larger picture of what happens with the Hawking radiation is an extension of that. But I just want to emphasize, I don't think this is something we are introducing by hand, which is some crazy postulate. It's something that that comes out naturally of calculations.
Yes.
Okay, so maybe this leads us into a natural segue into tomorrow's panel discussion, where I'm sure some of these topics will be continued and evolved further. Are there any other final urgent comments, or is everybody saturated at this point? And I get some thumbs up, so at least one person is saturated. In that case, let's say a big thank you to all of our panel members and to everybody else who contributed to a very stimulating discussion.
And for moderating it very well.
And thanks indeed. And see you all tomorrow.
Thank you, David. That was great. Bye. Yeah, thanks, guys. Thank you, everybody.
Thank you.
Until tomorrow.
Bye.